Okay, we should be live. Testing the audio. I've been talking to myself for a bit. Unless someone wants to join in. Unfortunately, there's a couple of things I have to do before we can get going. Okay, 1 second. Should be monitoring our audio and everything. Should be working. Okay, that's working okay. Don't like listening to my own voice. So yeah, we have this website that we develop. You know the drill. Go check it out. Just might also start the LinkedIn live stream. Problem with that one is that you need to manually set it up, because every time you get different stream key and URL and stuff, which is unfortunate. Don't like it at all, but it is what it is. We get most of our traffic off LinkedIn anyways. Yeah, if you did check the website and you have any questions, do let me know. There is a human in the loop. Well, just about. Yeah, I'll go over things in a sec. Yeah, obviously having the website in full screen makes things much better. But then you don't see the URL. Obviously, you can paste the URL in the chat. Give me a sec to turn this off. Yes, we should be going live on LinkedIn as well. Be live on LinkedIn as well. Yeah, I'm not sure where does that goes. Yeah, LinkedIn's a bit weird. It's quite a bit weird. Can't say I really like it. Give me a sec. Yeah, if you check the website, you have any questions, go for it. Oh, this is horrible. Yeah, LinkedIn. It's like recursive posting. Well, because I can't really. Well, I don't know. Probably just don't know how to use it. There is a problem of. Well, I need to mute those tabs as well, just in case. Yeah, the problem. There's lots of problems. Well, we love problems, don't we? If there was no problems, we will be out of a job. Yeah, all the analytics are quite distracting. Get to do something more useful than checking the analytics. I could use the analytics as turn it into a web application or something. Let's actually go notebook LM real quick. If there's no, so I'm checking myself, checking my sound. My sound should be okay. Yeah, well, my voice is not okay, but at least we're using the correct microphone, and that's a good start. That's a really good start. Actually, give me one sec. Okay, so for that, yeah, we can actually monitor chat on a different device. Don't worry about it. Don't worry about it. Oh yeah, we did notebook. Should we jump into notebook LM or try AI Studio chat to a bot? Because, well, if we have a human to talk to, that would be awesome. But humans are really good at pretending being busy. So fortunately or unfortunately, I'll have to be chatting to a bot. So we can do interaction thing. Interaction thing in Notebook LM. Shall we do that? So we give it the website. We also discover let's do Biomedical. Wait, no. Discover. Wait a sec. Yeah, how does Discover works in Notebook LM? Not sure. Not sure. Well, if we do the blurb, okay, so it gave us a YouTube video on our own site, which is fine. A notebook LM, what else we've got? So we untick that one, session biomedical tools. No. Wait, now I'm confused. Wait. We have it different screen. Just in case there's some copyright issues. Might be copyright issues. Okay, that's an interesting one. What's happening? Oh, a research article. Do we want a research article? It has all this AI generated stuff. This is in a Journal of Information System Engineering and Management. And it has all this AI generated images. And it's not only AI, it's bad AI. But yeah, let's keep that one. Doesn't say it's a PDF. Oh, there's some news article. Don't worry about it. Another boring article. Well, that's why we're using Notebook LM, because yeah, make it a bit more interesting. So we got 6 resources. And we have a special prompt for it as well. Okay, so we want to focus on our website. Another important prompt for a notebook LM is no fluff. It's no fluff. Yes, focus on BioniChaos. Okay, let's generate that. Yeah, we obviously are not reading any papers or anything silly like that. Hey, we essentially want a better version of that overview. We want a better version of that overview. It's funny that when I actually talk or show my face or whatever, the views actually go down. The views go down. Oops, sorry, my microphone got saturated. Yeah, that's another thing. It might be an issue with a human generating anything. Let's also try, while Notebook LM is generating stuff for us, let's share screen with AI Studio, so Gemini 2.5. Okay, can you review what's on the screen real quick?
Sure. What you're looking at.
Now we're having a problem. Okay, if we put it in a separate window or something, can you keep going? Keep going.
Okay, I see a web page with a title BioniChaos Biomedical. There's an audio overview at the top, and below that there are several tools listed, including a modality comparison bubble chart, a cochlear simulator, and an advanced EEG signal simulator. It seems to be a platform for biomedical tools.
Yeah, that's right. Can you keep reviewing? I'll just scroll down the page a bit.
Okay, scrolling down, I see more tools listed. There's an epilepsy and cardiac health and interactive evidence review, a synthetic noise generator dashboard, an interactive explorer for public multimodal biomedical datasets, an ECG simulator, and a brain-computer interface simulator. The page provides various interactive tools for biomedical research and education.
Okay, can you keep reviewing? Can you do a critical, take a critical stance? Don't mind dark humor as well.
From a critical standpoint, the website offers a variety of tools for biomedical data, which could be valuable for researchers and students. However, without further testing, it's difficult to assess the quality and usability of each tool. Also, the sheer number of tools might be overwhelming for some users, and the descriptions are quite technical, which might limit accessibility to those with a specific technical background. Additionally, the purpose and target audience for each tool could be made more clear.
Okay, yeah, I love you being critical. So, out of the tools that we covered so far, which one would you like to test?
Based on the descriptions, the Interactive Explorer Public Multimodal Biomedical Datasets seems like a promising tool to test. It allows for exploring various types of biomedical data, which could be quite insightful. It also mentions focusing on common data types like EEG and ECG, making it potentially useful for a broad range of users.
Okay, so this is the tool. What do you think?
This Signal Explorer tool looks promising. It provides an overview of different biomedical signal types and allows you to explore their characteristics and potential uses. It seems designed for educational purposes and to help users understand the strengths and weaknesses.
Okay, can you just get rid of the fluff and just be highly critical about it? Can you overview what is it you can see on the screen and what the buttons are doing?
The screen displays the Signal Explorer tool, presenting 4 buttons: EEG, ECG, PPG, and FNIRS. Below these buttons, there's information specific to the selective signal type, currently showing EEG details. The critical vulnerability is the tool's reliance on static information and predefined data. It lacks the ability for users to input their own data, perform interactive analysis, or explore complex scenarios beyond the provided examples. This limits its practical use for in-depth research or real-world applications, making it primarily a superficial educational tool. The buttons only serve to switch between preloaded signal descriptions, lacking any true interactive functionality for data exploration.
Okay, we actually have other tools for that, but I just scrolled down the page. Can you keep reviewing this particular tool and let me know what you think about it, how it can be improved, be highly critical?
Okay, focusing on the Dataset Deep Dive section, it provides a list of multimodal datasets with filter buttons for different signal combinations. While it's helpful to have access to these datasets, the critical flaw is the lack of direct integration with interactive analysis tools. Within this section, users might only view dataset descriptions rather than actively explore and visualize the data directly. To improve, integrating interactive analysis features within the Dataset Explorer, like the ability to plot signals or apply basic analysis tools, would significantly enhance its usability and practical value for data exploration.
Okay, just getting rid of the fluff will just sum this up. Can you just scroll down the page a bit further? Yeah, it doesn't fit the screen really well. But yeah, can you review the what you can see on the screen real quick? Be critical.
The current section titled The Core Challenges identifies 2 key hurdles in using multimodal data: ensuring high signal quality and managing incomplete data. It presents these challenges conceptually with a bar chart and a grid showing missing modalities. However, the critical drawback is the lack of practical solutions or interactive features within the section. It merely points out the problems without providing any interactive ways to explore or mitigate these challenges. To be more valuable, this section should include interactive simulations or tools that allow users to experiment with different signal quality or data imputation methods, providing a practical understanding of how to address these challenges, rather than just describing them.
Okay, so back to the main, back to the landing page. Can you again give a quick review of the tools out there, and which one would you like to test?
The landing page provides a variety of tools, including a modality comparison bubble chart, a cochlear simulator, an advanced EEG signal simulator, and various interactive explorers for biomedical datasets. Based on the previous discussion about the need for more interactive analysis, I would recommend testing the Interactive Explorer public multimodal biomedical datasets to see if it provides better interactive features for exploring and analyzing the data. This would allow for a more practical evaluation of how interactive features can.
Hey, we just did this right now. Can you just cut the fluff? Can you talk like a 30-year-old data scientist and yeah, suggest any other tools that we can review?
All right, let's cut to the chase. Since the Interactive Explorer for multimodal datasets didn't quite hit the mark for interactive analysis, let's take a look at the Advanced EEG Signal Simulator. It seems more focused on interactive exploration of EEG signals, allowing users to customize brainwaves and simulate artifacts. That could provide a more hands-on experience for understanding the data, which was a key limitation of the previous section. Let's check that one out.
Okay, this is what it looks like in a review real quick. Be critical.
All right, looking at the advanced EEG signal simulator, it's definitely more interactive than the previous tool. You can play around with different brainwave presets and simulate artifacts, which gives a much better understanding of how these signals behave. However, it's still a bit limited in terms of advanced analysis features. It's great for visualization and basic understanding, but real data scientists would need tools for more in-depth analysis, like advanced filtering, frequency analysis, and statistical measurements. Integrating those features would make this tool much more powerful and practical for serious research. Yeah, I got it. So, looking at the details, you've got brain state presets to simulate different brain states and artifact simulation to add muscle or eye blink artifacts. The page has several interactive components. The brain state presets drop-down lets you select different brainwave states. Below that, the artifact simulation sliders allow you to introduce muscle artifacts and eye blinks to see how they affect the signal. Further down, the fine-tune wave sliders let you adjust the amplitude of different brainwave frequencies, like delta, theta, alpha, and beta. On the right, the power spectrum and simulated EEG waveform display the effects of your adjustments in the frequency and time domains, showing you the frequency changes and the resulting EEG waveform. It's a good way to interact with EEG signals. Sure. The different brain state presets represent various cognitive states. For example, relax alpha. Right. So, relaxed slash meditative emphasizes alpha waves, which are associated with a calm but alert state. Light sleep slash drowsy, theta, highlights theta waves, typical of early sleep or deep relaxation. Deep sleep slash dominant delta focuses on delta waves, which are prominent during deep sleep. And focused concentration slash beta emphasizes beta waves, associated with active thinking and concentration. Each preset gives you a baseline to see the typical brainwave patterns in those states.
Okay, and what now I'm changing the artifact, the muscle artifact and the eye blink artifact. Well, you can't see the whole screen. We also have the time series domain. I don't know why it's not visible in one go kind of thing. It's to my display. But yeah, can you see it right now and review? Let me know what's happening in a critical way.
Yes, I can see the time domain waveform now. As you adjust the muscle EMG artifact slider, you can see the waveform becoming more jagged and regular, especially at higher levels. This represents the interference from muscle activity. When you increase the eye blink EOG artifact, you'll see larger, slower deflections in the waveform, mimicking the electrical signals caused by eye movements. The graphs show how these artifacts distort the underlying brainwave signals.
Right, and we meant to have like a play demo mode that just goes automatically through the different settings, adjusting each slider probably one at a time. Well, what do you think of that?
I think that's a great idea. A demo mode would make it much easier for users to quickly understand how each parameter affects the brainwave simulations. It would provide a guided experience, making the tool more accessible and intuitive to use.
And what else, if you had to review how this tool compares to other tools out there, either open source or commercial, like how would you go about it?
To compare this tool to others, I'd first identify its key features, like the brain state presets, artifact simulation, and the ability to fine-tune brainwave frequencies. Then, I'd look for other OEG simulators, both open source and commercial, and compare their functionalities. Key comparison points would include the range of features, ease of use, visualization quality, and the flexibility of the simulations. I'd also consider user feedback and reviews to assess the overall performance and usability of each tool.
And what other artifacts would you add?
Considering the artifacts panel, you could add simulations for other common EEG artifacts, such as electrode noise, which can appear as high-frequency interference, or movement artifacts, which cause larger, slower disruptions in the signal. Adding these artifacts would provide a more realistic and comprehensive simulation of EEG data, helping users understand the challenges of real-world EEG recordings.
Okay, and in terms of the preset states we have is deep sleep, light sleep, relaxed meditation, and focus concentration. What other preset brain states would you add?
You could add presets for different cognitive states, like active learning, problem solving, or even creativity, which might show different combinations of brainwave frequencies. Also, including presets for specific neurological conditions or varying levels of alertness, like high alertness or fatigue, could be very insightful for users. These presets would offer a broader range of scenarios to explore.
And how about the overview about at the bottom of the page? Can you? I'll just scroll through it. The? Can you summarize it real quick?
The overview at the bottom summarizes the simulator's purpose as an educational tool for exploring EEG signals and brainwave characteristics. It explains how it combines different brainwaves and artifacts to create synthetic EEG data, useful for learning, algorithm development, and understanding complex data. It also describes the different control panels and visualizations available. Finally, it mentions potential future enhancements, such as adding more waveforms, artifacts, advanced analysis, and real-time data import.
Okay, and how would you improve the description?
To improve the description, you could add more details about the specific parameters that can be adjusted and their impact on the simulated EEG signals. For example, explaining how adjusting the amplitude of different brain waves correlates with different mental states would be helpful. Additionally, providing more information on the technical details of the simulation, such as the algorithms used, could enhance the understanding for advanced users.
And do you have any, like looking at the simulator, do you have any critical questions about it?
One critical question would be about the accuracy and realism of the simulated brainwave patterns, especially for complex mental states. It's important to know how closely the synthetic signals represent real EEG data in various conditions. Another question could be about the limitations of the simulator, such as the range of artifacts it can simulate and the complexity of brain states it can model, compared to actual brain activity.
And just scrolling through the previous tool, the previous page, how does it compare to what we saw on the previous page?
This page provides a comparison of different biomedical modalities, including EEG, ECG, PPG, and FNIRS. Unlike the previous tool, which focused specifically on simulating EEG signals, this section gives a broader overview, describing the measured processes, temporal and spatial resolution, and common artifacts for each modality. It's more of a comparative and informational resource rather than a simulation tool.
Okay, and how does it compare to what you currently see on the screen? That's the landing page is pre-selected neurological web applications that we have. Can you give a quick overview, looking through it, give a quick overview? Don't mind you being critical.
This landing page presents a collection of neurological interactive tools and resources. Unlike the specific EEG simulator we discussed earlier, this page offers a variety of applications, including simulators for cochlear implants, interactive dashboards for medical data, and tools for visualizing and analyzing various brain signals. It provides a broader range of neurological tools, each with its own specific focus. A critical point might be to assess the depth and complexity of each tool, as they vary from simple simulators to more advanced data exploration tools.
We might finish that one. We had like 5.6 gigabyte in the browser for the AI Studio for this live streaming interaction. Let's move on to this. So we have a new overview of BioniChaos, and this should be comparing it to other resources out there. So, but yes, go check the website. Let me know if there are any questions. There's a human in the loop.
Imagine for a second a world where you could just think to your devices. No more fumbling with keyboards, no more trying to get your point across with, clumsy words.
Yeah, just direct thought.
Your brain directly connected, talking flawlessly to machines. Sounds like pure sci-fi, doesn't it?
It really does. But, for some people, it's actually starting to become a daily reality.
Right, thanks to brain-computer interfaces, or BCIs.
Exactly. And it's not just about, convenience, is it? This tech lets people regain abilities they've lost, control prosthetic limbs.
Or even just monitor their own cognitive state in real time.
Yeah, by bypassing all that messy, usual human communication stuff. It's a profound shift, maybe even a bit unsettling sometimes.
And that's exactly what we're diving headfirst into today. Welcome to the deep dive. We're unpacking the fascinating and, let's be honest, often chaotic world of biomedical signal processing.
Definitely chaotic at times.
Our sources for this one, they range from the real nitty-gritty of EEG data analysis, that's electroencephalography, to the incredible tech behind cochlear implants. Plus, we've got some interesting looks at how we actually understand all this incredibly complex data once we manage to wrestle it into submission.
Yeah. Wrestling is a good word for it. Our mission today really is to boil down the key bits from this whole intricate field, expose the raw challenges, and there are many that scientists and engineers face when they're dealing with the body's own signals.
And show you how human ingenuity tries, often against the odds, to make sense of the body's deepest, often really unruly whispers, that bionic chaos we were talking about.
Exactly, the bionic chaos.
Okay, so let's start at the start. What are BCIs, fundamentally?
Well, at their core, they're direct communication pathways, straight from your brain to some kind of external device.
Like a translator for your thoughts, almost.
Sort of, yeah. A super advanced one. And it opens up huge potential in areas like neurorehabilitation, say, for stroke patients.
Okay.
Assistive tech for people with paralysis, even things like gaming or monitoring cognitive status. It's all about using the brain's own raw language.
And when we talk about tapping into that language, EEG, electroencephalography, that seems to be the non-invasive rock star here.
It really is. It's powerful for understanding brain activity without cracking open the skull, which is,
A plus.
a big plus, yeah. Its advantages are pretty clear. High temporal resolution, meaning it catches those super fast brain changes.
Right.
It's relatively affordable compared to other methods, and, well, getting the data, the acquisition part, seems straightforward on the surface.
But seems is the operative word there, isn't it? Once you've got that raw brain data, you're really just at the starting line of a pretty grueling marathon.
Oh, absolutely. There's this standard kind of four-phase pipeline for analyzing EEG signals efficiently.
Okay, what's that?
It goes signal acquisition, getting the data, then signal pre-processing, cleaning it up, then feature extraction, finding the important bits, and finally signal classification, figuring out what it all means.
So it's this essential journey from just chaotic brain noise to something meaningful, some insight you can actually use.
Exactly. And believe me, that journey is rarely smooth. It's often bumpy.
I bet. And EEG, while popular, it's just one piece of the puzzle for catching these faint signals, right? There are other ways.
Yeah, definitely. Other non-invasive techniques give you different views, like magnetoencephalography, MEG,
Okay.
offers even higher spatial and temporal resolution. It directly measures the magnetic fields produced by neural activity.
Sounds powerful.
It is, but it's not portable. It's incredibly expensive, and you need this heavily shielded room, so not exactly practical for everyday use.
Yeah, not something you'd have next to your coffee machine.
Mm.
Then there's fMRI, functional magnetic resonance imaging.
Mm-hmm. We've all heard of MRIs. This one gives you really high spatial resolution, great for detailed brain maps, also non-invasive.
Right.
But again, huge machine, not portable, very expensive, needs that strong magnetic field. You're definitely not going for a jog with an fMRI strapped to your head.
Probably not even walking, no.
And then on the more portable, maybe more accessible end, you have NIRS, near-infrared spectroscopy.
Yeah,
It's affordable, non-invasive, you can use it for longer periods. The catch,
There's always a catch.
always, limited penetration depth into the brain, and it's slower, temporally, than EEG or MEG.
Okay. And what about invasive options?
Well, there's electrocorticography, ECOG. That gives you amazing signal quality because the electrodes are right on the brain's surface.
Wow.
But it requires invasive surgery, implanting that grid of electrodes. Effective, yes, but definitely not the first port of call. A big step.
Yeah, definitely a last resort kind of thing for many applications. And here's where it gets really messy, right? Even with EEG, the popular choice, analyzing the raw data, is described in our sources as extremely difficult.
Understatement, maybe.
Why is it so hard?
It's just this swirling mess of noise, artifacts, unwanted signals, and huge differences between individuals. One person's brain activity looks quite different from another's, even doing the same task.
And our sources mentioned this massive mechanical imbalance. What's that about?
Yeah, it basically means getting those electrodes to make good, stable contact with the scalp is really hard. Any tiny movement, sweat, muscle tension,
Yeah.
it can mess up the signal.
So it's like trying to eavesdrop on a tiny whisper
Mm-hmm.
from a single neuron, maybe, while standing in the middle of a heavy metal concert.
That's a pretty good analogy, actually. You have to
Yeah.
get really good at filtering out all the noise, the biological noise, the environmental noise, and sometimes the noise is way louder than the signal you actually care about.
Which brings us perfectly to that next crucial phase, signal preprocessing, the cleanup phase.
Exactly. And arguably the most challenging because those raw signals, they are, as one source puts it, frequently mingled with other kinds of undesired disruptions.
Nicely put. Disruptions we might call noise or artifacts.
Oh,
Sometimes humorously, sometimes maybe just painfully.
painfully, yeah. This is where the real fight against that BioniChaos truly begins. You have to tame it somehow.
What kind of artifacts are we talking about?
Oh, all sorts. Eye blinks and eye movements, they generate their own electrical signals called EOG artifacts.
Right.
Your heartbeat, the ECG signal, its electrical pulse, can bleed into the EEG.
Okay.
And just muscle movements, even tiny facial twitches, they produce electrical noise too. It's like this full-on biological symphony of interference.
And you're trying to pick out one specific instrument, like a single violin solo from that cacophony.
Precisely. It's tough.
So how do you do it? What's in the cleaning crew's toolkit?
Well, there's a whole arsenal of algorithms. A simple but often effective one is common average referencing, or AR.
AR.
Yeah, it basically subtracts the average signal across all the electrodes from each individual electrode. Helps reduce widespread noise.
Okay, makes sense.
It's good for improving the signal-to-noise ratio, but it struggles a bit if you don't have electrodes covering the whole head.
Right, like trying to clean a room by just averaging out the dirt only works if the dirt is everywhere.
Kind of, yeah. Then there's a more sophisticated one, Independent component analysis, ICA.
ICA. Heard of that one?
It's often praised because it can separate out those artifact signals from the genuine EEG signals without needing separate reference channels just for the artifacts.
That sounds useful.
Very. It's efficient for big data sets, which brain data usually is.
Mm-hmm.
But the math behind it, the decomposition process, can be really computationally demanding. It makes your computer work hard.
Okay. Powerful but pricey in terms of computation. What else?
Principal component analysis, PCA. It's a bit like taking a huge, messy report where loads of ideas are repeated or tangled up and boiling it down to just the essential, distinct points. Reduces complexity, helps reduce the number of features you need to deal with later.
So it simplifies things.
Exactly. Converts correlated data into uncorrelated components. One source we looked at had this kind of ironic comment. Though it is not as good as ICA, the PCA is still good.
Huh. Faint praise, maybe?
Maybe, but it's a classic, a reliable workhorse, even if it's not always the flashiest tool in the box.
Got it. Any others?
Sure. Common spatial patterns, CSP. This one's great for highlighting the subtle differences between different brain states. Really helps with classification later on.
Okay.
But it needs a lot of electrodes, and it's surprisingly sensitive to exactly where those electrodes are placed. A tiny shift can blur the lines again.
Tricky.
Very. Then there's surface Laplacian, SL. It tries to estimate the electrical current density flowing into or out of the scalp.
What does that do?
Improves spatial resolution, helps pinpoint where signals are coming from, and it's described as strong against artifacts.
Sounds good. The downside.
Its performance can really depend on these things called spline parameters used in the calculation. Basically, how smoothly you draw the electrical map. It's a bit of a precise art.
Right. And finally,
Adaptive filtering. Using techniques like LMS or RLS, these are really important when the brain signals you want and the artifacts you don't want overlap in their frequencies.
when they sound similar, electrically speaking.
Exactly. But, like many powerful tools, there's a trade-off. High computational complexity and sometimes slow convergence. You gain precision, but you pay for it in processing time.
So a whole suite of tools, each with strengths and weaknesses.
Absolutely. And using them effectively, choosing the right ones, that's crucial. These pre-processing steps, they're like the unsung heroes.
Yeah.
They ensure the data is as precise and clean as possible before you try to do anything meaningful with it.
Yeah.
Without this intense cleanup, trying to find patterns in that BioniChaos, well, it would just be a fool's errand.
Like trying to read a blueprint that someone spilled coffee all over versus a nice clean one.
Exactly that. You need the clean blueprint.
Okay, so we've acquired the signal, we've battled the BioniChaos, and pre-processed it, cleaned it up. Those chaotic whispers are a bit quieter now. What's next?
Next is finding the actual nuggets of meaning. This is feature extraction.
Feature extract.
Yeah, turning that cleaned up EEG data into a format that a computer can actually understand and use for classification.
Yeah.
Like recognizing if someone's stressed or happy or focused based on their brainwaves.
So pulling out the essence of the signal.
That's a good way to put it. And again, there's a whole toolkit of techniques, each suited for different things.
Like?
Well, there's adaptive autoregressive modeling, AAR. It's really good for features that change over time, adapting to those fluctuating, non-stationary signals you get in real brain activity.
Good at chasing a moving target, then.
Exactly. But it can be a bit sensitive to any noise that might have slipped through the cleaning process.
Okay. What about classics?
The fast Fourier transform, FFT. It's a staple for a reason. It converts the signal from the time domain, how it changes over time, to the frequency domain.
Why do that?
Because different mental states are often associated with specific brainwave frequency bands, delta, theta, alpha, beta, gamma. FFT helps you see the power in each of those bands.
Ah, like breaking down a complex song into the volume of its bass, mid-range, and treble frequencies.
Precisely. Its weakness, though. It mainly captures fixed signals, averaged over a time window. It doesn't give you much info about how frequencies change within that window.
So it gives you a snapshot, but not the movie.
Kind of, yeah. For more dynamic signals, the ones that change rapidly, we often turn to wavelet transform, WT, or wavelet packet decomposition, WPD.
Wavelets.
These are more sophisticated. They capture both time and frequency information simultaneously. They give you a much richer picture of non-stationary signals.
So you get the notes and the rhythm.
That's a great analogy. You see how the frequencies evolve over time? The trade-off, you guessed it.
Computationally harder.
Bingo. More
Okay.
complex calculations involved.
Okay. Any other interesting ones?
Definitely. Genetic algorithms, GAs, These are fascinating. They aren't directly analyzing the signal itself.
Oh,
No, they're optimization strategies. Inspired by natural evolution, they're used to select the best subset of features from all the ones you might have calculated.
so they help you choose which characteristics are most important.
Exactly. Finding the most pertinent characteristics, as one source put it, think of it like digital natural selection for your data features. Only the most informative ones survive to be used in the final classification.
Wow. Survival of the fittest data points.
Sort of. It can streamline the analysis and improve accuracy. But again, running these evolutionary processes can be computationally costly.
Seems like there's always a cost for power in this field.
Often, yes. It's about finding the right balance.
So you've extracted these optimized pertinent features. Now what?
Now we hit the final frontier, signal classification. This is where those clean, extracted features get sorted into meaningful categories.
The aha moment stage.
Hopefully. This is where you actually label the brain state. Is it relaxed, stressed, move left, move right, whatever categories you're aiming for?
This is where machine learning really comes into its own right.
Absolutely. Modern computer techniques, especially machine learning and deep learning, have totally revolutionized EEG analysis. They provide the algorithms that can learn the complex patterns linking features to specific brain states.
They're the brains behind the operation, decoding the signals.
Pretty much, moving us from just looking at squiggly lines to actually getting some genuine insight.
What kind of classifiers are common?
Oh, there's a whole zoo of them, each like a different kind of detective for your data. You have things like artificial neural networks, ANNs.
They're not so good.
They're pretty robust, good generalists for learning complex patterns, though figuring out the structure, like how many neurons to put in the hidden layers, that's often done by trial and error.
A bit fiddly.
Can be. Get it wrong, too few or too many neurons, and your classification accuracy can suffer. Too few, it misses things. Too many, it might overfit the training data and not work well on new data.
Right, like a detective seeing clues that aren't really there.
Exactly. Then you have support vector machines, SVMs. These are often really good at finding the optimal boundary to separate different classes of data. They frequently outperform other linear classifiers and offer good generality, meaning they work well on unseen data.
Sounds great. The catch.
High computational complexity, especially with very large data sets. They need serious computational muscle.
Okay. Powerful, but demanding. Anything simpler.
Sure, K, nearest neighbor, KNN. The basic idea is very easy to comprehend.
How does it work?
It classifies a new data point based on what the majority of its K nearest neighbors in the feature space are classified as. Simple to implement.
There's always a but.
Performance can be slow, poor runtime performance with large training sets. And it's sensitive to irrelevant features. Superfluous and unnecessary features can throw it off.
Like judging someone by their 5 closest friends, but maybe 2 of them are just random acquaintances who skew the picture.
That's a decent analogy, yeah. And of course, there are others too, like linear discriminant analysis, LDA, and naive Bayes classifiers, NBC, each with their own specific strengths and weaknesses.
It's incredible, really, how much information we can try and pull out of just the brain's electrical whispers.
It is. But the power of biomedical signal processing, it isn't just confined to decoding thoughts or emotions, is it?
No, absolutely not. Let's shift gears completely now to another really profound application that literally restores a human sense.
Right.
The world of cochlear implants and auditory digital signal processing.
A different kind of BioniChaos to manage.
Indeed. And this is crucial for people with sensorineural deafness, right? Where traditional hearing aids just don't work because the inner ear itself, the mechanism for translating sound vibrations into nerve signals, is damaged.
Exactly. In those cases, a hearing aid just makes the sound louder, but the damaged ear still can't process it. Cochlear implants are totally different. They're electronic devices designed to mimic the function of the damaged inner ear.
How do they do that?
Well, they typically have an external microphone and sound processor maybe worn on a belt or behind the ear now. And crucially, an electrode array that's surgically implanted directly into the cochlea, the inner ear.
Right into the structure.
Yes. The goal is to bypass the damaged hair cells and directly stimulate the auditory nerve fibers with carefully processed electrical pulses representing the incoming sound.
Wow. And development for these requires some serious research tools, I imagine.
Oh, for sure. One key tool mentioned in our sources is PICS.
PICS.
Stands for Programmable Interactive System for Cochlear Implant Electrode Stimulation. developed at MIT Lincoln Lab.
What's special about it?
It's flexibility. It lets researchers design and test totally new sound processing algorithms and, importantly, make real-time adjustments while a patient is actually using it in a clinical setting.
So you can tweak the algorithms on the fly. That must be invaluable.
Hugely. It allows for rapid prototyping and testing of different strategies. It's where the cutting edge really meets the human ear very directly.
And this flexibility allowed for some direct comparisons, right? And algorithm face-off.
Yeah, exactly. For instance, comparing the older InterAid systems strategy with a newer one called CIS.
Okay, what was the issue with InterAid?
The InterAid system used continuous analog waveforms to stimulate the electrodes. The problem was, if multiple electrodes were stimulated at the exact same time, their electrical fields could interact.
Leading to?
Spurious interactions, the source calls them. Basically, electrical crosstalk between channels, creating misleading artifacts or blurring the sound information. More chaos, but for your hearing.
Yeah, that sounds like it would make things harder to understand, not easier. A truly painful way to try and hear.
It could definitely muddy the waters. So the solution proposed was CIS, continuous interleaved sampling.
Interleaved, how does that work?
Instead of continuous waveforms, it uses trains of brief electrical pulses. And critically, these pulse trains for different electrode channels are interleaved in time, meaning only one electrode is active at any single instant. They take turns stimulating very rapidly.
Ah, so no simultaneous stimulation.
Exactly. That non-simultaneous stimulation drastically reduces the electrical interactions between channels. Makes for a much cleaner, potentially crisper signal getting to the auditory nerve.
Makes sense. Did it work? What were the results?
Well, it's interesting. In terms of just recognizing consonants in tests, the scores between the older InterAid simulations and the CIS simulations weren't always significantly different.
Oh, so CIS wasn't necessarily better on paper.
Not always on those specific tests, but, and this is key, when subjects listened to normal conversational speech, they showed a clear preference for the CIS simulation. It just sounded better, more natural to them.
That's fascinating. It highlights that subjective experience, the human side, matters just as much, if not more, than the raw scores sometimes.
Absolutely. Hearing isn't just about data points. It's about perception and quality experience.
And there was something about the number of channels, too.
Yes, a significant finding. One subject, SO4, scored an incredible 99% on a 24-consonant test using a 6-channel CIS simulation.
Wow, near perfect.
Compared to their performance with a 4-channel version. This strongly suggests that the number of channels used for stimulation has an important effect on performance.
So more channels, higher fidelity, a clearer symphony for the brain to interpret.
Seems that way. It's a powerful lesson in the value of providing more detailed information when you can do it cleanly.
Amazing stuff. But, all this incredible data, whether it's from EEG or cochlear implants, all this sophisticated processing, it's kind of useless if we can't understand it.
Or communicate it effectively, yeah.
Which brings us to that crucial final step, making sense of it all, making this complex scientific and biomedical data comprehensible.
Not just for other scientists who, speak the jargon, but for clinicians, patients, maybe even the wider public. It's the ultimate translation challenge, perhaps.
And one approach focuses on the art of clear vision. We looked at Martin Bohr's work on data visualization for biomedical scientists.
His whole philosophy is about clear vision and clear understanding, trying to bridge that gap between dense, often intimidating scientific output.
Yeah, those graphs that look like a tangled mess of lines and dots.
Exactly. Bridging that gap to create visualizations that actually provide insight, that are digestible.
He had a specific innovation mentioned, the null zone.
Yes. It's a really clever method for visualizing statistical error or uncertainty, instead of using traditional error bars, which can get cluttered and confusing, especially with many data points.
Right, little I-beams everywhere.
Yeah. He uses a simple gray bar representing the range where the result is not statistically significant, the null zone. If your result falls outside that gray bar, it's significant.
So it's immediately visually obvious.
Much more intuitive. He talks about balancing removing ink, Tufts' idea of minimizing visual clutter while still providing clear signposts for the viewer. It makes checking for statistical significance way easier.
That's smart. Moving from just numbers to a clear visual cue.
Exactly. And beyond static graphs, there are other ways to make complex info accessible. We also looked at resources like neuroscience education interactive video tools.
What kind of tools are these?
Things like interactive 3D brain models you can rotate and explore,
Cool.
actual cadaveric slices, videos of neurological exams being performed, even real patient case studies presented interactively.
So it's like a different kind of data processing, taking raw knowledge and transforming it for learning and practical use.
Precisely. It's about bridging the gap between didactic information and real-life clinical presentation, taking the abstract concepts from textbooks and making them tangible, relatable, clinically relevant.
Making the academic intimately real.
Yeah. Bringing that often messy, real-world complexity of biomedical science into a format that truly educates and informs, whether you're a doctor, a student, a researcher.
Or just someone listening to this deep dive, curious about how we make sense of our own internal BioniChaos.
Exactly. It's all part of the same challenge.
Wow. What an incredible journey we've taken today. Seriously.
Yeah.
From those chaotic whispers of raw brain signals from EEG,
The initial mess.
through that painstaking pre-processing, the algorithmic cleanup crew, battling the BioniChaos,
Yep.
then extracting features, classifying states,
Yeah.
all the way to the sophisticated signal processing that helps restore hearing with cochlear implants, creating a clear internal symphony.
A huge range of applications.
And then finally, landing on the crucial art and science of making all this profound work understandable, digestible. Because really, if you can't share the knowledge, what's the point?
That's right. It's a field that's just constantly advancing, isn't it? Always pushing the boundaries of what's possible and how humans and technology interact.
It really is. And it's clearly a messy, complex process.
Yeah.
Lots of trial and error, dealing with the inherent unpredictability, the BioniChaos of the human body.
Definitely. It meets cutting-edge engineering, complex algorithms, sometimes even an artistic touch and visualization. But underlying it all is this incredible drive, this desire to improve people's lives.
Yeah. Which leads to a final thought, maybe slightly provocative one. If our brains are now starting to talk directly to devices, and devices are helping us bypass damaged senses like hearing, what's the next fundamental human sense, or maybe even ability, that we'll try to decode, enhance, or maybe even replace with technology?
That's a big question. Vision, touch, memory.
Who knows? And maybe more importantly, what kind of ethical noise and artifacts will that particular deep dive have to pre-process?
Oof. Yeah, that's a whole other layer of complexity, isn't it? The ethical BioniChaos, something to definitely think about.
Okay, so there is a human in the loop. If you have any questions, I'm actually torturing Gemini to see what else it can do. It's meant to be an independent component analysis. A simulation doesn't make sense anymore, so we might. Yeah, doing a lot of like physics. Okay, so there is a human in the loop. Oops. Yeah, so we're torturing Gemini, see what it can do. It's really good at making physics simulators, like gravity simulators and the like, applying physical formulas. So we're doing the same thing for biomedical data, and simulations are quite interesting, like quite relevant, because you can benchmark your, well, code generating a AI, whatever it is, whichever model you are using. You can just have your prompts. We have a problem with the sound. The tone.js is not loading correctly. I don't know why. Gemini can fix something like that. Should be fairly basic. I'm actually wondering if it will work okay on locally on my machine. It actually probably will. And what else we've got? We actually did a different version of it. Doesn't work. Does it work? No. Yeah, anyway, it's pretty good at doing things like that, whatever you like. Yes, we did a review. Yeah, Notebook LM, that's what you heard before, was doing a review of BioniChaos in relation to whatever other sources it found, but yeah, it went places. It wasn't great. Would not be using it as a standalone anything. Yeah, I want to focus on things like this. I'm just not sure why it doesn't make sense. So in the chat, can you explain, without changing the code yet, can you explain why this web application doesn't make much sense? So particularly, well, to begin with, we don't want to be adding sources manually. We would like some sort of preset that just works. And then when we click PCA and ICA, we somehow needed to be absolutely clear which one is currently being displayed on the screen. So we want the visualization of independent component analysis and PCA as well. We want to be able to learn about the difference between them. Currently the simulation games seem to be highly basic, very rudimental. So we want to, yeah, the noise is working really well. Yeah, the reset works. Yeah, I'm not sure. I haven't tried the audio yet. I assume it's working okay. But we don't want to damage our hearing. Now the window size is weird. The window size seems to be too narrow, too short. So we might need to address that. I don't know if we need a control. What would you suggest? So just in the chat, without modifying the code, can you overview what's going on and make any suggestions based on what we discussed? We have a bit of a delay. Well, the problem if we read it using a Gemini is pretty painful. I'll actually pop it into Notebook LM real quick.
Of course. That's excellent, detailed feedback, and it gets right to the core of how to turn this from a simple demo into a powerful educational tool. Let's break it down point by point, explaining the current state and how we can address your suggestions. 1. The problem: manually adding sources. Current state: you're right. The current design requires the user to manually click Add Source Mode and then place sources on the scalp. This is tedious and assumes the user already knows what kind of brain state they want to simulate. It puts the burden of creating a meaningful scenario on the user. Suggestion: implement preset scenarios. Instead of the Add Source Mode button, we could replace it with a set of preset buttons that instantly configure the simulation. This would be much more effective for learning. For example, Preset 1: Relaxed, alpha dominant, automatically adds one strong alpha wave source, common when someone is relaxed with their eyes closed, and maybe a little background beta. Preset 2, active task, beta dominant, adds a strong beta source and maybe some gamma, simulating a brain that's actively thinking or problem solving. Preset 3, noisy data, adds one or two weak sources but turns the noise level up high. This would be a perfect scenario to show how Ika can pull a hidden signal out of what looks like pure static. Preset 4, complex mixture, adds 4 to 5 different sources at once to demonstrate how chaotic the raw signal can become and to showcase the power of the analysis tools. This change would immediately make the simulation more focused and guided. 2. The problem, PCA and Ika clarity. Current state, the last update added labels and color coding, which was a step in the right direction. However, as you've noted, it isn't absolutely clear what's happening. The visualization needs to more actively teach the difference. Suggestion: enhance the visual feedback loop. Clearer mode indication. When you click, apply PCA, or apply ICA. A large, clear title could appear above the waveforms, like PCA mode, components sorted by variance, or Ika mode, independent sources unmixed. This removes all ambiguity about what is being displayed. Interactive highlighting, the aha.
Yeah, so if you make another request, it stops playing. So we get Notebook LM to do the thing as well. Yeah, Notebook LM is generating forever, but it's much better. It's something you can actually listen to, as opposed to a robotic voice within a Gemini.com. And as if you haven't checked BioniChaos.com yet, go do so real quick and provide your questions, your feedback, complaints, requests, subscribe, unsubscribe, stuff like that. Okay, what's that? Getting raw signal. Okay, if we have active, we have 3 components. Does it even make sense? Okay, raw signal and noisy data. We have 1 source, complex mix. Okay. And why the source is coming from outside the head? Okay, can improve. Yeah, a longer time scale does work better. If we apply PCA, also we have those 8 PCA, PC1 to PC8, and when we do ICA, we get these 4 sources. Do they even make sense? Does it make sense? Well, it assumes they are alpha, beta, theta, delta, but it's meant to be the location. What? Meant to be the location on the head. Let's reduce the noise quick. The residual noise. No, it doesn't work well. Obviously, it's just a simple simulation, but yeah, I wouldn't even know how to explain it properly. Let's actually let's throw a kitchen sink at this. And let's bring another a prompt engineer. Let's bring a prompt engineer. Okay, what is it you are looking at?
looking at a video of an interactive simulation of a brain EEG, specifically demonstrating ICA mode, which is for separating independent sources.
Okay, so when we reset the simulation, what happens? And let me know if it makes sense.
When the simulation is reset, it goes back to showing the raw EEG signals from 8 channels, which are a mixture of different brainwave frequencies and noise. It essentially starts the process of demonstrating how ICA can separate these.
Okay, now when we hit...
When you hit the Apply ICA button, the simulation applies the independent component analysis algorithm to the raw EEG signals. It then displays the separated brainwave sources, like alpha, beta, theta, and delta, along with any residual noise.
No, wait, can you explain? So when we reset the simulation, there's no sources, is that correct?
That's right. When you reset the simulation, it goes back to showing the mixed raw EEG signals from the channels, not the separate brainwave sources. The sources are only displayed after you apply the ICA algorithm.
No, so we first need to select a preset like relaxed or something, relaxed state, is that correct? And now we have 2 sources. Can you explain what's happening?
Yes, you first select a preset like relaxed to generate the raw EEG signals with specific characteristics. Then, when you apply ICA, the simulation separates those mixed signals into their independent sources, which you see displayed as distinct waveforms.
Okay, so the 8 channels that are recorded, can you explain what the montage is? Like what is a montage and what is it in this case? Can you explain it properly?
The montage refers to the placement of electrodes on the scalp and how the signals are recorded. In this simulation, it shows 8 channels, likely representing different electrode positions on the scalp, each recording a mix of brainwaves activity from the underlying brain agents.
Okay, looking when I scroll through the timescale controller, do you think the maximum and the minimum time window are adequate, or would you change it?
The timescale controller allows you to adjust the time window for viewing the signals, which is useful for examining both slow and fast wave patterns. The current range seems adequate for observing different brainwave frequencies, but depending on the specific analysis, a wider range might be useful for very slow or very fast signals.
Okay, never mind. Then what happens when I switch between the presets? So now it's relaxed, active task, noisy data. For some reason I only have 1 source, and then I have this complex mix. Can you explain what's happening to the sources? And mainly, why is it that some of the sources are outside the head? Can you explain that?
When you switch between presets like relaxed or active task, the simulation generates different combinations of brainwave frequencies and noise to represent various mental states. The number of sources displayed represents the independent sources the ICA algorithm identifies. Some sources might appear inside or outside the head in the simulation as a way to show their estimated spatial distribution or origin based on the electrode placements, even if they aren't precise anatomical locations.
Can you be a bit more critical about this?
All right. While the simulation provides a good visual demonstration of ICA, it simplifies the complexity of real EEG data. The spatial representation of sources is an estimation and may not accurately reflect the true brain activity, as ICA has limitations in precisely localizing sources. Additionally, the predefined presets might not capture all the nuances of real-world brain activity.
So how would you change it to make it better?
To improve the simulation, it could incorporate more realistic brainwave patterns and noise sources, possibly based on actual EEG data. Enhancing the visualization to show more accurate source localization with confidence intervals could also make it more informative. Additionally, allowing users to customize the parameters of the simulated sources could provide a more interactive and educational experience.
Wait a sec. So can you explain one thing? So first of all, yeah, it's really weird that some of the sources are outside the head. That's not very realistic, is it? Unless we're talking about the noise coming from the room where the experiment is conducted. And then, yeah, can you also explain why when I'm applying ICA, I have four sources and they're not spatially differentiated but they seem to be differentiated by the different frequency bands. Can you explain that?
You're right. Sources appearing outside the head isn't physiologically accurate for brain activity. It likely represents noise or artifacts that the ICA algorithm identifies as independent sources, which might be originating from external interference or other factors. Regarding the sources being differentiated by frequency bands instead of spatial location when applying ICA, the algorithm aims to separate mixed signals into independent components. These components might exhibit distinct frequency characteristics, and the simulation might be visualizing them as separate sources based on these frequency differences, rather than purely their spatial location on the scalp.
Okay, can you make it simpler and also suggest improvements to the simulation?
In simpler terms, the simulation shows how ICA tries to separate mixed brain signals into individual sources. The sources outside the head are likely noise, and the different frequencies represent different types of brain activity. To make it better, the simulation could use more realistic brain data, show more accurate source locations, and let users adjust the settings to explore different scenarios.
Okay, and also, so in the presets, can we have like a manual preset where you could actually place sources with your mouse on top of the head? How does that sound?
That's an excellent idea. Adding a manual preset where users can place sources directly on the head would make the simulation much more interactive and educational, allowing them to explore different source configurations more effectively.
So would you have the current presets relaxed, active task, noisy data, complex mix, and then another manual button? Is that what you're thinking?
Yes, exactly. Having a separate manual preset button alongside the existing presets would give users a clear way to choose between predefined scenarios and creating their own custom source configurations.
Okay, and how about how would you, if you had to improve the time scale, what would you change? The maximum time windows seem to be too short at the moment.
To improve the timescale, we could increase the maximum time window to allow users to view longer segments of the brain's activity. This would help them observe slower patterns and understand the dynamics of the signals better.
Anything else you would do with this web application to make it better and clearer?
One more improvement could be to add clearer labels and explanations for the different modes and functions. This would make the simulation more accessible to users with less technical knowledge, helping them understand the concepts more easily.
Yeah, any questions are welcome. There is a human in the loop, just if you were wondering. But go check
Thank
out
you.
the website first.
Sure, I'm here to help whenever you're ready. Feel free to explore the website and come back with any more questions you might have.
Yeah, this is the website we're developing.
It looks like you're building a platform with various biomedical tools and simulations. That's a great initiative for education and research. How can I assist you further with this website? The current EEG simulation fits well with your platform's focus on biomedical data, technology, and education. It provides a valuable tool for users to learn about brain activity and how ICA works, aligning with your goal of providing interactive tools for researchers, educators, and students.
Welcome to the deep dive. Today, we're tackling something really interesting. We're basically taking apart the user feedback for a pretty cutting-edge tool.
That's right.
Our mission is to figure out how we learn about, well, ourselves specifically, those super tricky signals from our own brains.
Mm-hmm.
We've got some great source material here. It's essentially detailed notes on turning a brainwave simulation demo into something genuinely useful, something really insightful for learning.
Exactly. And there's a neat little paradox here as well.
Oh, yeah.
Well, it's a tool designed to show you what's happening inside your head.
Right.
But the feedback makes it crystal clear that the outside interface, how you interact with it, needs a major overhaul. It needs to be, clearer, more guided.
Okay, let's unpack that.
Okay.
Because look, brainwave simulations sound incredibly cool, right?
Very sci-fi.
They do. But the reality sometimes is that you're just staring at what looks like TV static. Total data jumble.
Uh-huh. It can be overwhelming.
So our sources map out those exact pain points where people get stuck or confused. And then, the brilliant part, they offer these often really simple fixes to turn that static into a real aha moment.
Making the invisible visible. essentially.
Exactly, and making the chaotic make sense.
Yeah. All right, let's kick things off with what the sources flag as a big initial hurdle. Like right out of the gate, the manual setup.
Yes, the setup.
Right now, the design makes you click add source mode. Then you have to manually drag and drop these virtual brainwave sources onto a 3D scalp model. And the feedback, it doesn't mince words. It calls it tedious.
It is a bit fiddly.
And more importantly, it sort of assumes you already know exactly what brain state you're trying to build.
Which most learners probably don't, right? That's the whole point of using the tool.
Exactly. So it puts the whole burden of creating a meaningful scenario, as they put it, squarely on you, the user.
And that's critical because that initial fiddliness, that barrier, it actually gets in the way of the learning it's supposed to enable.
Well, it's like being handed a guitar kit and told to build the guitar before you can learn your first chord.
Okay, yeah.
You get bogged down in the mechanics, the setup, before you even get close to understanding the music, or in this case, the neuroscience. It adds this cognitive load right at the start.
So you're fighting the tool instead of learning from it.
Precisely.
Okay, so if that's the problem, this DIY setup nightmare, what's the fix? This is where it gets clever, I think.
It really is.
The idea is to ditch that add source mode button entirely and replace it with preset scenarios, simple buttons.
Right. So instead of building from scratch, you just click a button and bam, the simulation is instantly configured for a specific, common, and educationally useful brain state.
It flips it from a chore to an instant learning opportunity.
Exactly. And it guides you. It lets you immediately see and even hear what different brain states are like, which is way more powerful than just reading a description.
And the specific presets they suggest are really well thought out, not just random examples. They're teaching tools in themselves.
They are. Let's run through a couple.
Okay, like preset 1, relaxed, alpha dominant. You click that.
And it instantly sets up a strong alpha wave source. That's that classic eyes closed, calm, maybe slightly meditative state.
Right, the brain's chill mode, maybe with a little background beta noise just to show you're still, conscious.
Exactly. Establishes a nice baseline.
Then there's preset 2, active task, beta dominant.
Uh-huh. Click this, and you get strong beta waves, maybe some faster gamma mixed in. This mimics the brain when it's really focused, like solving a math problem or concentrating hard.
So you immediately see that higher frequency, more energetic activity.
You do. It shows focus.
Okay, but preset 3 is my favorite. It's got this, dark humor element to it. Noisy data.
Yes, the realistic one.
Right. This one adds maybe 1 or 2 weak brain sources signals that are barely even there, and then it cranks the background noise way up high.
So it looks like garbage data, basically. Pure static.
Exactly. And the whole point is to perfectly set the stage for showing off how a tool like ICA, which we'll get to, can actually pull that tiny hidden signal out of all that noise.
It's the needle in the haystack scenario.
Totally. Finding a whisper in a hurricane, it's brilliant because it demonstrates the problem before showing the solution.
And then the last one mentioned is preset 4, complex mixture.
Right. What's that one do?
This one just throws, say, 4 or 5 different sources onto the scalp at once, all firing away.
Okay, chaos mode.
Pretty much.
Huh.
The idea isn't clarity here. It's to show you just how messy and complex the raw signal from the scalp actually is when lots of brain areas are active together.
So it justifies the need for the fancy analysis tools.
Precisely. It demonstrates why we need things like PCA and ICA
Big
to
time.
untangle that neural mess.
Yeah.
It really drives home their importance.
Got it. So moving to presets isn't just about making it easier. It makes it focused, guided, and sets up specific learning moments right from the start.
Couldn't have said it better myself. It channels the user towards understanding.
Okay, next step. The sources flagged an ongoing issue with clarity around 2 key analysis methods. PCA, principal component analysis, and ICA, independent component analysis. Apparently, even with recent updates like adding labels and colors, it's still, and I quote, not absolutely clear what's happening.
Yeah, and that's a crucial point because understanding the difference between PCA and ICA is fundamental here.
What is the core difference in simple terms?
Well, PCA finds mathematical components that explain the most variance in the data. They're abstract, ordered by statistical importance, but they don't necessarily map cleanly onto the real underlying brain sources.
Okay, so it simplifies the data based on math.
Right, whereas ICA's goal is different. It tries to unmix the signals to find components that are statistically independent, which often correspond much better to the actual distinct sources of activity in the brain, like finding individual voices in a mixed recording.
Gotcha. Real sources versus mathematical constructs. And if the simulation doesn't make that distinction super clear,
then the user misses a huge conceptual leap.
yeah.
They might think PCA is finding real things in the same way ICA is, which isn't quite right.
So how do we fix that ambiguity? The suggestions here seem really smart, focusing on visual feedback.
They are. The first step is just clearer labeling in the moment.
Right, like big, bold titles that pop up dynamically. So when you switch modes, you see PCA mode, components sorted by variance, or ICA mode, independent sources unmixed. No mistaking what you're looking at.
Simple, but effective. Reduces ambiguity instantly.
But the really cool part, the interactive aha moment, comes next.
This is the clever bit, yeah.
Okay, so get this. When you're in ICA mode and you hover your mouse pointer over one of the separated waveforms at the bottom, let's say it's labeled est, source 2, alpha. The original source that you, or the preset, placed on the virtual scalp model, the one generating that alpha wave, it actually lights up. It glows or pulses.
Yes.
It creates this direct visual link. You hover over the result, and it shows you the origin on the scalp model. It's like magic. It visually proves that the algorithm successfully found and isolated that specific source from the mix.
Exactly. It makes the abstract concept of source separation tangible, interactive. You see the connection. It's not just graphs, it's discovery.
And then the genius part is how this plays out for PCA.
Right, the contrast.
With PCA, if you hover over one of its components, nothing lights up on the scalp.
Correct.
And that lack of a highlight is the teaching moment.
Precisely. The absence of the glow subtly reinforces the PCA components are different. They're mathematical summaries, not direct representations of those localized brain sources in the same way the ICA components often are.
So the interaction itself teaches the core conceptual difference. That's really elegant.
It uses the interface itself to deliver the lesson, which is great design.
Okay, next problem area, the time window. Right now, how much time you see on the brainwave display is fixed. You can't change it.
a fixed view.
But the feedback rightly points out that the timescale is a critical parameter for EEG analysis. You need to be able to adjust it.
Absolutely. Think about it. Brainwaves happen at very different speeds. You've got slow waves like delta, maybe 1 or 2 cycles per second associated with deep sleep.
Right, very slow.
And then you've got super fast gamma waves, maybe 40, 50, even 100 cycles per second, linked to complex processing.
Okay, big difference.
Huge. And if your viewing window is too short, you won't see the full shape of the slow waves. If it's too long, the fast waves just look like a compressed blur. You lose detail.
Like trying to watch a snail race and a hummingbird flap its wings with the same camera speed.
Exactly. You need to adjust the shutter speed, or in this case, the time scale, to see each one clearly.
So the proposed fix, again, seems elegantly simple, a slider.
Yep. Just add a timescale slider, maybe right next to the existing noise slider. Keep it intuitive.
And sliding it left would zoom out, right? So you see more time, more waves packed onto the screen.
Perfect for spotting those long, slow delta or theta patterns. You see the bigger picture of the rhythm.
And sliding it right would zoom in.
Correct. You see less time overall. The waves are stretched out, showing more detail. Ideal for really examining the shape and frequency of those fast beta or gamma waves.
So it gives you, the user, direct control to explore the data at different resolutions.
Exactly like a real neuroscientist would do. You zoom in to see the fine details, zoom out to see the overall patterns. It empowers you to actively investigate the data, not just passively look at it.
Makes perfect sense, turning a static display into an interactive microscope for time.
Well put.
All right, before we wrap up, there's one last point, a quick one, that the source has brought up. Audio safety.
Ah, yes. Good to address.
Now, when you think brainwave simulation audio, you might imagine, I don't know, crazy sci-fi zaps or intense static surges, right?
Yeah.
Maybe something dramatic?
You might expect that, yeah. Maybe some brain-melting rock concert based on gamma waves.
Exactly. But thankfully, the feedback confirms that's absolutely not what's happening here.
No, definitely not. The current implementation keeps the volume extremely low. The gain is capped at 0.1, which is just 10% of the maximum possible volume.
Okay, so very quiet.
Very quiet.
Yeah.
And the whole point isn't high-fidelity audio entertainment. It's sonification.
Sonification.
Just representing the data patterns as sound in a subtle way.
Yeah.
Maybe pitch changes with frequency or volume with amplitude, something like that. But the priority is absolutely safety and comfort.
Right.
No sudden loud noises, no jarring static bursts. It's meant to be an informative layer, not something that startles or annoys you.
Okay, good to know. So we don't need to worry about accidentally blasting our eardrums with our own simulated alpha waves.
No neural noise assaults planned, no. Just gentle data sounds.
Ooh.
Mm.
Okay, so wrapping this up then. We've taken a depth dive into some really critical smart improvements for this brainwave simulation.
We have.
We went from that tedious manual setup to these clever guided presets that actually teach you something right away.
A huge improvement for usability and learning.
Then we looked at making the difference between PCA and ICA crystal clear, using not just labels, but that really cool interactive highlighting.
Turning an abstract concept into a visual interactive discovery.
Yeah, that hover effect is brilliant. And finally, giving users that crucial control over the timescale, letting you zoom in and out on brain time itself.
Empowering exploration.
So, if you put all these pieces together, what's the big picture here?
Well, these changes, they really elevate the simulation. It stops being just a basic demo and becomes a genuinely powerful, interactive learning environment.
Right.
It's about taking this incredibly complex, invisible world inside our heads and making it visible, audible, and most importantly, understandable. It bridges the gap between abstract neuroscience concepts and intuitive experience.
So as tools like this get better and better, letting us simulate and maybe even debug the brain's signals, it does raise a kind of weird question, doesn't it?
What's that?
Well, if we get really good at this, if we can perfectly simulate and identify all the separate sources, all the independent components firing away in there, what happens to our idea of a single unified you? Does that feeling of being oneself just become the sum of its perfectly unmixed parts?
That's a deep one. Does understanding the components diminish the whole?
Right. Something to think about. If we can map all the voices, where does the conductor sit?
A fascinating thought to end on.
Indeed. We hope this deep dive gave you plenty to mull over. Until next time, keep exploring, keep questioning,
And keep diving deep.
Okay, there is a human in the loop. If you have any questions, go for it. But also check out the website. What did we review? Yeah, we have Advanced EEG Signal Simulator. Actually have a review on that one. Yeah, let's do that one next. Unless there's a human, another human in the loop. Really cool. So this is an intended for training and learning. Yes. Obviously, Gemini would have had a much longer response. Sure, what's happening with my YouTube and LinkedIn, whatever, the streams. I don't know what the delay is as well. There might be some long delay. But yes, they're intended for training and learning. Does it support real sensor input? Well, depends what you refer to as a sensor. Well, the site has things that using as sensors is your keyboard, mouse, your vision is a good sensor. No smell, hopefully. Well, if you can smell anything, that's probably because the GPU is doing too much work and your machine is on fire. Sensor input to analyze brainwaves. Yeah, if you were an LLM, which I assume you are, I would have asked to elaborate on the prompt, make the prompt more specific. But no, this is obviously synthetic data. Well, I'm not sure if it's obvious or not. This is synthetic data. But yes, we have some other tools that use real data. But that would have been pre-recorded. Like this data here is pre-recorded EEG from epilepsy patients. What else we've got? Yes, we're training our models. Let me know if you're interested in that. Happy to talk about that. Well, yeah, because the cost of some EEG devices is quite astronomical. I supposedly you can get a Neurosky for $99. I think it's US, and I think it's not true anymore. I think you used to be able to get it. Yeah, you can go to the... Well, it's not a sponsored video. I don't think it's true. Okay, we're not going into personal medical conditions. I'm more than happy to talk about epilepsy in more general terms. Yeah, there's a lot on epilepsy on this channel. I did my research on it. Yeah, we actually trained the network to detect seizures, which was actually quite successful. There's no misclassified images in this case. But yes, that could not be applicable to a different data set. So if you actually upload your data, it doesn't mean it will work. It was fine-tuned. The dataset is public domain, 600 images. My code is public domain as well. So what are we using? NumPy, Pillow, TensorFlow. Yeah, the usual suspects. There's a write-up on the results. And you can see the results of each run of training that we did. And some of them, yeah, didn't do so great. So in this case, you had the two, was it false positives and 3 false negatives or the other way around. Let me know if you'd like me to explain that. Yeah, there should be a lot more on epilepsy data. What kind of brainwaves active during vivid visualization? Higher gamma, lower theta? Don't know. What's that brainwave active? Vivid visualization? You mean like hallucination? So yeah, we have this tool here, which I'll probably drop some frames during the streaming, just because it's a bit heavy. Yeah, dropped about 700 frames. But this tool here, it doesn't show well on this display. Crazy. So you have the brain. Yeah, the zoom. So you have your brain. Well, it's not your brain, obviously, but we have a brain. And then if we have, say, visualization, vivid visualization, well, assume talking about what's it called? Loss of vision. We used to have muscle stiffening, auditory, yeah, say auditory hallucinations. So they will appear in this region of the brain. Which type of brain waves those will be, well, it doesn't really matter. It just means that this area of the brain will be more active in one way or another. If it's higher gamma, lower theta, whatever, yeah, it's not normally not clinically relevant, but it depends what recording you're doing. This one will be like an fMRI combined with EEG. I don't know. Again, this is just simulated stuff. And yes, you can simulate a light sleep. We can add vivid visualization. I don't know if the bot will be able to do it correctly or not. Doesn't really matter for simulation purposes, but what do we have currently? Deep sleep, light sleep, deep sleep. Yeah, you have mostly delta. Should be fairly correct, I think. Light sleep, yeah. Dreaming is lower, but I wonder, dreaming is lower. Deep sleep. Well, you would be dreaming in deep sleep, wouldn't you? So it would be lower, yeah. Dreaming is lower, but I wonder if intentional visualization is different or similar to dream brainwaves. Yeah. Going places now. Yeah, I'm trying to stay fairly scientific. We can ask the bot, it will go on and on talking about it if you like. But we are going places. I can't even see. I have this like laugh heart overlaid on top of the chat on my phone. I wonder if lower brainwaves would be more like a carrier wave made up of smaller but high frequency activity that contains more data. Yeah, it's not that complicated. I mean, yeah. Your model of the world will define how you view these things. Yeah, the implementation of the models probably be even more important. Well, the thing is, once you have this delta, theta, alpha, beta, whatever, once in real world it will be different anyway. You will have high overlaps between things, so yeah, that's what your time series will look like on each channel, and that's what we're trying to do at the moment, is to try this independent components analysis. So if you had your complex whatever sources, then you're trying to distinguish what are they. Well, in theory you can. Reality, good luck, you cannot. Yeah, I'm not sure if you have any specific questions to let me know. Probably have to go check out the website first. Yes, if you are interested in neurological stuff, yeah, go this drop down, select neurological EEG, neurotools. You'll have a bunch. Of a bunch of stuff. Yeah, don't forget to, smash that like button. Subscribe, unsubscribe. You know what to do. I think I have a lot of subscribers who are not watching the content, so they might as well. Yeah, unless there's more questions from a human. Well, when you put something in the chat, I still assume you're a robot, but if we have any good questions, happy to take them. There is a human in the loop. I got the PhD in biomedical engineering, so should kinda know. Never trust anyone, but yeah. Good luck. Sorting out information, but we might move to the board because I actually get more views when Notebook LM is pretty good. We'll be talking about enhancing EEG simulation and analysis. Yeah, it's one of those. It's meant to be. Wait. Okay, I got mixed up with my. Yeah, let's do this one. It's short, 6 minutes.
Ever stop to think about those tiny electrical whispers happening inside your head right now? The signals buzzing in your brain.
Mm-hmm.
Today, we're diving into an EEG signal simulation app. More than that, though, we're looking at how to take it from just okay to, well, genuinely useful and realistic.
Right.
Our mission, really, is to explore how you could turn a basic demo into something much more robust.
Yeah.
A proper educational tool.
Yeah, moving beyond like perfect textbook waves.
Exactly. We're talking about going from that theoretical neatness to the wondrously messy reality of actual brain data.
And the fascinating part is this journey makes some pretty complex neuroscience feel, I think, way more accessible, maybe even, dare I say, fun to play with.
Fun, yeah.
Giving you, the learner, those real aha moments when you see how it all connects.
Okay, so to get those aha moments, the sources are pretty clear. We need to start with the critical part, embracing the mess. Real EEG isn't clean, is it?
Oh, not at all. It's kind of plagued by signals that aren't brain signals. We call them artifacts.
Right. Things getting in the way.
Exactly. And to make a simulation feel real, you have to include them, like eye blinks, EOG. Big, slow waves. You mostly see them messing with the front electrodes.
Okay.
Then there's muscle noise, EMG. That's more like high-frequency crackling, especially near the edges of the scalp, jaw clenching, things like that. And the classic one, line noise. Just this constant low-level 60 hertz or 50 hertz, depending where you are, sine wave.
Yeah.
Like electrical interference humming along under everything.
So adding that noise, ironically, makes the simulation better. It makes that noisy data preset actually more realistic.
Absolutely. And it perfectly sets up why tools like ICA, independent component analysis, are so powerful.
Because they help you sort through that mess.
Precisely. You use ICA to try and pull apart those different signals, the blinks, the muscle noise, the actual brain activity. It shows you how to clean things up.
Okay. And does seeing that separation help with figuring out where the brain signals are coming from? Source localization.
It's a step towards it, yeah. Instead of just showing activity on a flat 2D circle of the scalp, The idea is to hint at a 3D brain inside. Okay,
Right.
so maybe when ICA is active, you could show like a simple 2D glass brain view, top down or from the side.
And it would show the estimated source.
Yeah, maybe with a little shaded area, a kind of semi-transparent confidence interval around it. So it's not just here it is, but we're pretty sure it's somewhere in this region. More honest.
Right, acknowledging the uncertainty. So we've got the realism, the messiness. How do we make it more uh, interactive, more fun?
This is where you get to be the architect.
Okay.
Imagine in the manual mode, you click on a source you've placed on this virtual brain, and maybe a little menu pops up or slides out.
What would that let you do?
Well, that's the cool part, deep customization. You could choose the exact brainwave type you want, alpha, beta, gamma, whatever, maybe from a drop-down list,
Uh-huh.
and then use, say, a slider to fine-tune its strength, its amplitude. Suddenly, you're not just placing a generic source, you're designing a specific brain state.
That sounds much more engaging.
Yeah.
And then the sources mentioned something even more game-like, a challenge mode.
Yes. This is where it gets really fun, I think, turning the learning into a bit of a puzzle.
Okay, like what kind of puzzle?
Well, imagine a challenge called Find the Source. The simulation gives you a mixed-up signal, maybe with some noise added in,
Right.
and your job is to use the tools, probably ICA, to find a specific hidden brainwave, like, okay, find the hidden alpha source in this mess.
I like that. Any others?
Or denoise the signal. You'd see data clearly contaminated with a specific artifact, like a big, obvious eye blink pattern.
Okay.
And the challenge is apply ICA, find the component that is the eye blink, and maybe isolate it or remove it. It makes understanding what ICA actually does feel like solving something concrete.
That definitely sounds more engaging than just reading about it.
Yeah.
Now, beyond just seeing the raw waveforms, what about understanding their frequency content?
Ah, yes, absolutely crucial. You need a frequency spectrum plot, usually done with an FFT, a fast Fourier transform. It's a standard tool.
Okay, and what would that show you in the simulation?
It would be a real-time graph, basically showing how much power there is at different frequencies. So if you set the simulation to a relaxed state,
You'd expect to see alpha waves.
exactly, you'd see a clear peak in the plot right around 8 to 12 hertz. Then switch it to an active task state, and you'd see that peak maybe shrink, and another one pop up in the beta range, like 13 to 30 hertz.
So you visually confirm the brain state change in the frequencies. That's a neat aha moment right there.
It really is. Direct visual feedback.
And finally, tying it all together, making sense of the controls and the concepts, the idea of a context-aware information panel.
Right. Sort of merging the how to use guide with the what is EEG background info.
How would that work dynamically?
Yeah, the panel would just automatically update based on what you're doing or looking at. Click the Apply ICA button. The panel pops up a simple explanation of what ICA is and what it's trying to do.
Or hover over something.
Sure. Hover over the alpha option in that manual mode menu. It tells you briefly what alpha waves are typically associated with. It makes learning feel less like homework and more like discovery right there in the moment.
Integrated learning.
Uh-huh.
I like it. So wrapping this up, what's the big takeaway for you, the curious learner, looking at this?
Well, we've basically walked through how you can take a simple simulation and make it much richer, turn it into a proper interactive educational
I know,
platform.
surprising details, yeah.
And I think the key is embracing that real-world complexity, the noise, the artifacts, and then giving you the tools to actively explore and manipulate the signals.
Making those core ideas of EEG processing feel much more accessible and hopefully pretty engaging.
Yeah, exactly, making it less abstract, more hands-on.
So here's a final thought to leave you with. If we can make understanding something as complex as brain, signals this interactive, this tangible, what other invisible processes, maybe inside your own body or even out in the world, could we start to demystify using this kind of simulation power? Ever wondered what's really buzzing inside your skull? I mean, what if you could actually peer into your brain? Not with some invasive probe, obviously, but maybe with like a digital control panel.
Yeah, like literally dialing up different states of consciousness.
Exactly. So today we're doing a deep dive into electroencephalography, or EEG, but not just any EEG. We're exploring these, well, surprisingly powerful and sometimes kind of hilariously flawed digital tools.
Tools that let us play virtual mad scientists, right? Conjuring synthetic brainwaves and seeing what happens.
You got it. Our journey into this digital neuroscience lab, it's powered by two main sources we looked at: detailed bits from an advanced EEG signal simulator, and then this broader thing called BioniChaos, an interactive biomedical toolkit overview.
Okay.
And our mission today is pretty clear. Figure out how these synthetic signals can, demystify the brain's complexity. What are they actually for?
And critically, where do these tools really nail it? Or maybe where do they spectacularly miss the mark?
Precisely. It's not just about brainwaves. It's about the tools we use to understand ourselves. And, well, sometimes those tools have a few. Let's call them quirks.
Delightfully ironic quirks, perhaps.
Let's hope so. All right, so to get into this, maybe lay down some basics first. Like, what is EEG, fundamentally?
Right. So at its core, it's non-invasive. It just records the electrical activity humming away in your brain. We call the signals brainwaves.
Okay, brainwaves.
Yeah, and they're really the synchronized symphony of massive groups of neurons all firing together. It's the brain's electrical hum, basically.
Gotcha. So where do synthetic EEG signals fit in then?
Okay, this is where it gets really interesting. These are artificially generated waveforms. They're designed very carefully to mimic real brain activity.
So like a digital twin of your brain's chatter.
Pretty much, yeah.
Huh.
But with one huge difference. You are in control. Total control. You can isolate one specific brainwave, like pulling out just the trumpets from that symphony, or, mix and match them however you want.
Okay, but why? Why go to the trouble of making fake brain activity when, there are plenty of real brains around?
That's the key question. And the answer is they're incredibly useful for learning and education, for starters.
How so?
Well, students, researchers, they get an intuitive, hands-on way to understand how different brain states, focus, relaxation, sleep, actually look in the data, both in the raw signal over time, the time domain, and in terms of the underlying frequencies, which you see in the power spectrum. It simplifies the often really messy, chaotic look of real data, gives you a clean baseline.
So it strips away the noise, the real-world messiness to let you see the building blocks clearly.
Exactly. And then think about the engineers, the data scientists. For them, this is like an essential sandbox.
A playground for algorithms.
Absolutely. If you're developing tech that interacts with the brain, this is crucial. You can test and validate really complex signal processing algorithms.
Like what, for example?
Think about algorithms for automatically removing artifacts like eye blinks or muscle tension from EEG recordings. Or even cooler, building and refining brain-computer interfaces, BCIs.
Right.
They can test all that against what we call a reliable ground truth, a signal that's perfectly controlled, totally predictable, because they designed it.
No surprises from a subject suddenly deciding to twitch or yawn.
Precisely. You just can't get that level of precision and reproducibility with real human data sometimes.
Okay, so tools like these promise a window into the brain's electrical world, fake or real. Our initial search led us to this bigger platform called BioniChaos, which honestly sounds pretty cool.
Yeah, the name has a certain ring to it.
And the description sound like a gold mine. Modality comparison bubble chart, cochlear simulator, ECG simulator, like everything you could want.
The marketing definitely set expectations high. Maybe a little too high.
You think? What was the reality?
Well, what's fascinating, or maybe, darkly amusing, is the gap between the promise and what it actually delivered. While it looks valuable, when you dig in, it's actually quite overwhelming. The descriptions are super technical, full of jargon.
So not very accessible unless you're already deep in that specific field.
Exactly. It kind of limits who can actually use it. And it's hard to tell up front if any particular tool is actually any good or, useful. Felt less like a coherent toolkit and more like a big, messy digital drawer you have to rummage through.
A digital junk drawer, maybe, hoping for diamonds, finding rusty spoons.
That's a pretty good analogy, yeah. And one thing in that drawer, the Interactive Explorer for Public Multimodal Biomedical Datasets, really caught our eye initially.
Yeah, the name alone sounds like exactly what you'd want for exploring data, right? EEG, ECG, all sorts.
It sounded like the Holy Grail. But this is where the source material gets pretty critical, almost scathing, actually.
Oh, how so?
Despite the fancy title, the tool relies almost entirely on static information, predefined data sets. You can't upload your own data.
Wait, really? No user data.
Nope. And you can't do any real-time interactive analysis or explore scenarios beyond what's already baked in. The source calls it a superficial educational tool.
Superficial. Ouch.
Yeah, you click buttons and it just switches between preloaded text descriptions or maybe shows a static graph. It's not an explorer, it's more like a very nicely organized but totally static digital brochure.
Wow. So you're shown the data, but you can't actually do anything with it.
Pretty much, like being promised a spaceship and getting a really detailed blueprint instead. Looks nice, but you're not going anywhere.
Okay, that is disappointing.
And the irony gets deeper. It has this core challenges section, which, sounds good. It correctly points out big hurdles in working with multimodal data signal quality issues, missing data points, real problems.
Okay, so it identifies the problems.
Yeah, but that's all it does. It just points them out. It offers zero practical solutions, no interactive features to help you actually deal with those problems, no simulations, no troubleshooting tools built in.
So it's basically, here are the problems, good luck.
Exactly, which is remarkably unhelpful for something calling itself a toolkit.
Right. So after that enlightening tour of BioniChaos, we were definitely hoping for something more interactive, more hands-on. We wanted a lab, not just a library catalog.
Understandably, we needed something that actually let you get your hands dirty,
Yeah,
digitally speaking.
Do not despair, because this is where the deep dive took a much better turn. We found the advanced EEG signal simulator, and it felt different right away.
Yes. This one actually felt like a proper tool, like that mad scientist's lab, but, cleaner and less likely to explode.
Yeah. The design is immediately much more intuitive. Controls on the left, visualizations on the right. You tweak something.
And boom, the graphs update instantly. Real-time feedback. It makes abstract concepts feel really concrete, really visual.
And the interactive bits, that's where the real fun starts.
Wow.
They have these brain state presets.
Yeah, those are great. Quick ways to simulate common mental states, like you hit relaxed meditative.
And you see strong alpha waves pop up.
Totally.
Right? That calm but alert state.
Exactly. Then you can switch to light sleep drowsy, see the theta waves start to dominate, early sleep, deep relaxation.
Or deep sleep for those big, slow delta waves.
Right. And then focus concentration brings out the beta waves, active thinking, problem solving. Each preset is like an instant baseline for that state. A quick dial for consciousness modes.
But it's not just clean signals, is it? What really got me was the artifact simulation. It embraces the mess.
Oh yeah, this is crucial because real EEG is messy. You can dial in muscle artifact, EMG, high-frequency noise.
From like clenching your jaw.
Exactly, or tensing your neck, and you see the waveform get all jagged and noisy, just like it does in reality. It shows you how muscle activity can just swamp the brain signals.
And the eye blinks too. EOG artifact.
Yep. Big, slow wave spikes every time the simulated person blinks. It's actually kind of shocking how massive that electrical signal is from just a simple blink.
Almost comical, like you said. It really highlights how much interference there is.
And learning to recognize those artifacts is such a critical skill if you ever work with real EEG. This simulator lets you see them clearly, turn them on and off.
Beyond the presets and artifacts, there's the fine-tune waves part. Real granular control.
Totally. You can independently adjust the power, the amplitude of delta, theta, alpha, beta. Mix your own perfect brainwave cocktail.
Ooh, a brainwave cocktail. I like that.
There's even a customized mode for getting super precise with frequency and bandwidth. It really puts you in the driver's seat for signal design.
And to help make sense of it all, there are the spectrum overlays, those dotted lines.
Right. They show the ideal pure shape for each brainwave type. So you can easily compare your cocktail mix against its perfect theoretical ingredients. It's a really smart visual aid.
Okay, so you make all these adjustments, you craft your cocktail. What do you actually see on the screen?
Good question. Two main visualizations on the right. First, the power spectrum. That's the frequency domain graph.
The result of that fast Fourier transform thing.
Exactly. FFT. It mathematically unpacks the signal, breaks it down into its component frequencies, shows you how much power or energy is at each specific frequency. That's where you see clear peaks for the dominant brainwaves, like an electrical fingerprint.
Okay. And below that?
Below that is the simulated EEG waveform, the time domain graph. This is the raw moment-by-moment voltage. The combined signal with all the waves and artifacts you added, all summed together.
So that's like watching the digital brain think in real time. The raw electrical ebb and flow.
That's a great way to put it, yeah. It's the complete picture, the full mess, moment by moment.
Now, connecting this back, you mentioned something really interesting, that the final mix signal, the blue graph.
The signal spectrum, yeah.
Right. It often doesn't perfectly match those dotted ideal overlays, even if you try to isolate just one wave type.
Exactly. And this isn't a bug or a flaw in the simulator.
That's a feature, a lesson.
Precisely. It's demonstrating a fundamental concept, interference. Think about mixing, I don't know, musical notes. The dotted overlay is like a single pure note played alone, but when you play multiple notes together to make a chord or mix multiple brainwaves, they interact. They interfere.
How so?
Well, sometimes their peaks line up and add together, making the signal stronger there. That's constructive interference. Other times, a peak from one wave meets a trough, a dip from another.
And they cancel each other out?
Partially or even fully, yeah. That's destructive interference. So the final combined signal, that cocktail,
It ends up being more complex and lumpy than any of its individual parts.
you got it. It's the messy, complex reality of combined signals. It's designed that way to help you understand how even pure, perfect components add up to create something more realistic, more, well, lumpy.
A dose of reality, served digitally. I like the irony.
It's a really powerful way to learn how signals actually combine in the real world where nothing is ever perfectly clean.
So let's pull this together. What's the verdict on this advanced EEG signal simulator?
Well, look, it's clearly a huge step up from something like the BioniChaos Explorer. It is interactive, it's intuitive.
Yeah, it genuinely seems to demystify EEG, giving you that granular control showing the link between time and frequency. It feels like a proper dynamic learning environment.
Definitely. It's a great digital sandbox, like you said, really useful for beginners getting the hang of EEG concepts, but also for practitioners who want to maybe refresh their understanding of signal composition. It earns the advanced in its name, I think.
But there's always a but, isn't there?
Yeah.
What are the limitations, especially for, say, serious researchers?
Right. For the real data scientists, as the source puts it, or seasoned neuroscientists, while it's fantastic for visualization and building intuition, it's still a bit limited in terms of advanced analysis features, meaning they'd likely need more sophisticated tools, things like advanced digital filtering options, more complex statistical analysis methods, maybe source localization algorithms to estimate where in the brain the signals are coming from. Those aren't really built in here.
So it's a great teaching instrument, maybe less of a full research bench.
That's a good way to put it. It's educational, but maybe not quite a full-fledged research workstation on its own.
Did the source suggest ways it could become that? Future directions?
Oh yeah, thoughtfully so. They talked about adding more brainwave types, like gamma waves. Those are linked to higher level thinking, conscious perception. That would be cool.
Yes.
More artifact types. This is where it gets really gritty. Simulating EKG interference from the heart.
The heartbeat showing up in brain signals.
Exactly. Or power line noise, that 50 or 60 hertz hum you get from electrical wiring. Electrode noise. Even complex movement artifacts, like someone just shifting their head slightly.
Wow, simulating that level of real-world noise would be intense. Really test your artifact removal skills.
Totally. It would mimic the brutal reality of collecting clean EEG data much more closely.
Any other enhancements mentioned?
Yeah, things like adding spectrograms, those let you see how the frequency spectrum changes over time, which is super important for dynamic brain states, and multi-channel simulation to look at how different brain areas connect and communicate.
Connectivity, right.
And the sort of ultimate goal they mention, real-time data import. Imagine uploading your own messy EEG data and comparing it side by side with these perfectly controlled simulations.
Okay, that would be a game changer. Turning it from just a simulator into a powerful comparative analysis tool.
Exactly. So yeah, it's a fantastic educational platform now for building that core understanding, a great digital sandbox, but don't expect it to interpret your actual brain scan results or replace high-end research software just
Yes,
yet.
the brainwave blender, not the full industrial mixer. Got it.
Good analogy, but for understanding the ingredients in the cocktail, it's invaluable.
So quite a journey. We went from this overview of biomedical toolkits, some promising interaction, others well, surprisingly static.
Yeah, the digital brochure incident.
Right. To this really quite fascinating deep dive into synthetic EEG. We've seen how this digital brainwave blender can make the brain's electrical chatter less mysterious.
And how even these precise simulations have that messy, interfered cocktail quality, just like the real thing, a kind of controlled chaos, which is strangely appropriate for the brain.
It is, isn't it? Which maybe leads to a bigger thought.
Go on.
Well, if we can generate these artificial brain signals so convincingly, understand their parts, manipulate them, how close does that get us to really understanding the actual brain, or maybe even influencing it?
That's the million-dollar question, isn't it? And what does it mean for things like consciousness if its electrical fingerprint can be mimicked so well, maybe even generated just by software?
Yeah, it definitely gets the neurons firing. Or maybe just the circuit boards whirring, like you said.
It's a deep thought to chew on.
Absolutely. So maybe something for you, our listener, to think about. What are the implications of these powerful simulation tools? Could other super complex systems, maybe climate or economies or social dynamics, benefit from this kind of synthetic simulator approach, turning overwhelming chaos into something you can actually grasp?
Perhaps the next big breakthrough isn't always in analyzing the real thing directly, but in building a really, really good fake first.
Food for thought. Thanks for diving deep with us today. All right, let's unpack this. Imagine trying to get the real secrets from someone's mind, but it's buried under just loads of static, you know.
Like tuning an old radio, yeah.
Exactly. So today, we're doing a deep dive into cleaning up that raw brain data. We found this really interesting method from a YouTube source, BioniChaos. It's all about getting clarity from, well, chaos.
It really is. We're looking at something super practical here. Noise reduction in EEG. That's the brain's electrical chatter.
Right.
And specifically using something called wavelet transforms to do it. It's, well, getting clean data is everything in this field, obviously. And this tool, it seems to offer a pretty direct way to tackle that noise. No frills, just results.
Yeah, it looks surprisingly straightforward. Let's talk about the front panel they show.
Yeah.
How does it actually let you manage the noise so precisely?
Well, you've got some neat controls, like you can stop it auto-playing the data, which is handy.
Okay.
And crucially, you can select just a specific bit of the recording. The source mentions picking a segment with higher delta frequency.
Right, delta frequency. Now, for maybe folks like me or listeners not steeped in brain waves, what's the significance there? Why target delta?
Good question. So delta waves are typically associated with deep sleep or sometimes certain brain issues, maybe injury or anesthesia.
Ah, okay.
So if you're studying sleep or trying to separate normal activity from something else, isolating those delta-heavy segments is key. You don't want that specific activity smearing over everything else.
Makes sense.
And the tool recognizes that, some channels will pick up more delta than others. Depends on where the sensor is on the head.
So it's electrode-specific almost.
Exactly. And you can tweak things like window size, basically how much data you're looking at in one chunk.
Like adjusting your focus.
Sort of, yeah. And you can even overlay the whole spectrum, see all the frequencies dancing around at once. It helps you spot where the noise really lives.
Okay, so that's how you find and target the noise. Pretty granular control. Now, the actual cleanup, the wavelet denoise algorithm. That sounds like the core engine here.
It is. That's the magic, really.
And you can just switch it on and off, which is interesting. And it defaults to using something called discrete wavelet transform.
Correct. That's a common type. But the key thing you mentioned is the levels.
Yeah, the levels. The source noted that beyond 10, it doesn't make much difference. What's that about? Is 10 levels some kind of magic number?
Oh, maybe not magic, but it's a really insightful observation. Think of levels like layers of analysis. Each level breaks the signal down further, looking for finer and finer details or patterns.
Okay.
What that beyond 10 comment suggests is a point of diminishing returns. You can keep breaking it down, adding more levels, but after about 10, you're not really getting much more clarity.
Just more computer work, maybe?
Pretty much. You hit this sort of efficiency ceiling. It's about finding that sweet spot, enough detail to clean the noise, but not so much that it's overkill or takes forever. Crucial for research you want to actually finish.
Right. Efficiency matters.
Absolutely.
Right.
And the goal, like the source shows really clearly on another channel example, is that stark difference, noise present, then noise removed.
You see the before and after.
Exactly. It's not just fiddling with settings, it's actually transforming messy, maybe unusable data into something clear, something that tells you what's really going on.
It's pretty remarkable, honestly,
Yeah.
how a tool can make something so complex, like analyzing brain signals, feel, well, manageable. It cuts right through the noise to the actual signal. Less fluff, more substance.
Definitely. And you know what? It makes you think. If we can get this good at stripping noise from brain signals, what about all the other noise in our lives? The noise in data we see every day, noise in how we perceive things, even noise in how we communicate.
Right. Like information overload or bias.
Exactly. What important signals, what critical insights are we maybe missing because we don't have our own kind of personal denoise algorithms running? What clarity are we leaving on the table?
That's actually a pretty deep thought to end on. Filtering out the noise in our own heads and in the world.
Imagine the brain, not just, the physical thing, but this incredible electrical symphony happening inside. Billions of neurons firing. It's vast, it's noisy, it's fascinating.
It really is an absolute orchestra.
But here's the tricky part, right? How do you possibly listen to just one instrument, say, one specific thought process, when that whole orchestra is playing full blast? And maybe there are a few broken instruments making noise too.
Yeah, that's the core problem we're getting into today.
Exactly. So this deep dive, it's all about exploring an interactive EEG simulation, electroencephalography.
And our mission, really, is to unpack how scientists use these mathematical tools to try and untangle those incredibly mixed up brain signals.
We want to give you a clearer picture, shortcut the overwhelm maybe, of these complex analytical tools like PCA and ICA.
Make it almost feel simple, even though the math behind it is anything but.
And we've really dug into how this specific simulation works. It's clever bits, it's surprising limitations.
Oh yeah, like finding brain activity outside the head. We'll get to that. It's quite something.
Right. And also the ingenious ways people are trying to make these simulations even better. It's really a look at the critical thinking involved in just trying to make sense of brain chatter.
Definitely.
Okay, so let's start with the basics of this simulation. You open it up, and first thing you see are these raw EEG signals.
The gate channels.
Right. And looking at them initially, it's just kind of chaos.
It is. It's absolutely a jumble. It's a mixture of all the different brainwave frequencies, your alpha, beta, theta, delta, all mashed together, plus, a good amount of noise.
So what are we really seeing there? Is it like listening to a crowded room?
That's a perfect analogy. Imagine one microphone stuck right in the middle of a really noisy party. You don't hear individual conversations clearly. You just get this wall of sound.
A mixed signal.
Precisely. That's raw EEG. Each electrode on the scalp picks up a blend of whatever electrical activity is happening underneath it.
And the montage, that's just where you put the electrodes.
Well, it's where, but it's also the specific pattern. It's strategic. Different montages give you different views, different ways of comparing activity between brain regions, because each channel records that unique mix.
Okay, that makes sense. So you have this jumbled signal. How does the simulation show different mental states, like relaxed versus focused? Does it have built-in examples?
Yeah, it uses presets. Things like relaxed or active task. These aren't random. They generate specific, predefined combinations of those brain waves and noise levels.
Ah, so it gives you a starting point.
Exactly. It shows you what a relaxed state might look like in terms of its typical frequency mix and noise, Even before you try to clean it up, it sets a baseline.
Right. So we've got the noisy room, the jumbled signal. The big question then is, how do you find the individual voices, the actual brain patterns hidden in there?
This is where the cool tools come in. The mathematical superheroes, as you put it. Principal component analysis, PCA, and independent component analysis, ICA.
Oh.
They're both designed to tackle this exact problem. Unmixing the signals, sticking with the noisy room analogy.
Yeah.
PCA is like having a sort of magical microphone. But instead of finding individual speakers, it points itself at the loudest thing happening in the room.
The biggest source of
It's
sound.
the biggest source of variance, technically. So maybe a loud argument in one corner, it captures that first. Then it finds the next loudest thing that's as different as possible from the first one. Maybe some music playing.
So it's about overall energy, not specific voices.
Exactly. Directions of maximum variance. It organizes the sound by its dominant statistical patterns.
Okay, so that's PCA. What about ICA? You said it goes further.
It does.
Yeah.
ICA is more sophisticated. It actually tries to unmix the signals to isolate each individual speaker.
Ah, okay.
It looks for signals that are statistically independent of each other.
Mm-hmm.
It asks, mathematically, what are the distinct, separate sources that when you add them all together, create this jumbled mess we started with?
That sounds much closer to what you'd actually want to do with brain signals.
In many cases, yes. It's incredibly powerful for trying to separate out the underlying brain activity or even identifying noise sources.
And the simulation visualizes this really well, doesn't it, when you switch to PCA?
Yep, the waveforms on the screen change. They all turn one neutral color, like white or gray.
Signaling that these aren't direct electrode readings anymore.
Right. They're abstract components.
Yeah.
And you get labels. Component 1, max variance, component 2, and so on. It's visually obvious that component 1 has the most energy in the next, going down the list.
An ordered list based on energy. Got it.
Mhm.
But then ICA. This is where it gets really clever, I think, and quite intuitive visually.
It is pretty neat. When you apply ICA, the output channels, the unmixed signals, their colors, actually match the colors of the original sources you set up on the simulated scalp.
So if you had a blue alpha source simulated on the head,
The unmixed waveform that the algorithm thinks is that alpha source also shows up blue. It creates this direct visual link.
and the labels change too, right?
They do. Critically, they say something like est, source 1 alpha. That est, for estimated, is really important.
Why's that?
It reminds you that ICA is making an educated guess. A statistically informed separation, but still an estimate. It's not perfect biological truth.
Okay. And there's that interactive bit too.
Oh yeah, the highlight. If you hover your mouse over one of those unmixed waveforms, like the estimated alpha one,
Yeah.
the original source location on the little head model actually glows.
Ah, that's
It
brilliant.
really drives home the connection. It shows you visually, look, the algorithm found this signal which corresponds to that source we put in. It's very satisfying.
And I have to say, I appreciate the honesty of the simulation too. The channels that don't seem to match a clean source.
They get labeled residual noise, and they're usually grayed out.
It's like ICA just pulls out the good stuff and leaves the junk behind, which, let's be honest, is what you always hope for with real data.
Uh-huh, absolutely. If only real data were always that clean.
Okay, now for the, let's call it the slightly weird part, the ironic twist. You mention sources appearing outside the head in the simulation.
Yes. This is one of those things that makes you pause and think. You can sometimes see, based on the ICA results, sources seemingly localized, well, in the air next to the head.
Which obviously isn't where brainwaves come from.
Right. Physiologically, that makes no sense. Your brain activity stays inside your skull, thankfully.
So what is it picking up then?
It's most likely picking up noise or artifacts, things that the ICA algorithm identifies as being statistically independent sources.
Like what kind of things?
Could be external electrical interference. That 60 hertz hum from power lines is a classic one. Could be muscle activity, maybe from jaw clenching. Could even be eye movement artifacts. ICA finds something that's independent, mathematically speaking.
And just sort of maps it somewhere, even if that somewhere is physically impossible.
Exactly, and that's the irony, isn't it?
Mm-hmm.
A simulation designed to model the brain ends up finding signals that seem to come from nowhere near the brain.
It's a bit of dark humor for data analysts, maybe. A reminder that algorithms follow the math, not necessarily the biology.
Precisely. It's a fantastic teaching moment, actually. It highlights that ICA and tools like it primarily separate sources based on their statistical properties, like their frequency bands and independence, not just their physical location.
So if there's a strong, independent noise signal,
ICA will likely pull it out as a component, and the visualization might place it somewhere odd. It really underscores that you can't just blindly trust the output. You need that human expertise to interpret it, to ask, does this actually make sense?
Right, distinguishing mathematical possibility from biological reality.
You got it.
Which brings us to the limitations. Recognizing these quirks is crucial because, look, this simulation is great visually, but it is a simplification, right?
Absolutely. Real EG data is infinitely more complex and messy. The spatial mapping in the simulation is just an estimation. Those presets don't capture every nuance. It's a fantastic starting point, but it's not the full picture.
So naturally, people always want to make it better. There's this ongoing quest for improvement based on feedback.
Yeah, and the wish list really highlights the challenges neuroscientists face every day.
One big one seems to be just adding more realism. More realistic brain patterns, yes, but also more realistic noise.
Oh, definitely. The request to add buttons to simulate common artifacts, that's my favorite bit of practical dark humor.
Like adding an eye blink button?
Exactly. Or a muscle tension button for EMG noise, or line noise for that electrical hum. Because, honestly, what's brain analysis without wrestling with all that junk?
You don't really appreciate clean data until you've seen how messy the real stuff is.
So true.
Yeah.
Then there's the visualization side. People want better source localization, maybe with confidence estimates. How sure are we it's there?
And that top-down head map, the topo plot.
Yeah, a topographical plot that's standard in the field. It shows voltage across the whole scalp surface with colors. Very intuitive.
What about more advanced stuff like ERPs, event-related potentials?
That would be cool. Like having a button to simulate a quick flash of light, the flash stimulus, and another button, average trials.
And you'd click it lots of times.
And slowly, out of the noise, this tiny little waveform, the brain's response to the flash, would emerge. That's how ERPs are found, averaging away the noise to find the signal locked to an event. It's like finding a ghost in the machine.
Wow. Okay. And more user control too, I imagine.
Always. People want to tweak the simulated sources, maybe even place them manually on the head model, a manual preset mode.
And that time scale thing, being able to zoom in or out on the time axis.
Crucial. A timescale slider lets you see both slow waves, like delta, and faster ones, like beta, more clearly. Addresses that feeling that the default view might be too narrow or too wide sometimes.
Makes sense. And then there's making it fun. Gamification.
Yeah, suggestions like challenge modes, like find the hidden alpha source or clean the signal, where you have to identify and maybe filter out simulated artifacts.
Or match the state. Try to recreate a drowsy brain state using the controls.
Exactly. It turns it from just a demo into more of an interactive puzzle. Really helps with learning.
And the good news is a lot of these improvements have actually been put into the simulation over time, right?
Oh, definitely. Many of the things we just talked about, the presets, the time slider, the clear mode labels, that awesome interactive ICA highlighting, the manual source placement, they're often already implemented in current versions. It shows it's an evolving tool.
Which is great to see.
And just a quick practical note, if you ever play with the audio feature, some versions have the sonification.
Yeah.
The volume is usually kept very low, intentionally. It's more about representing frequency as pitch, not about blasting you with loud static. Safety first.
Good tip. Don't want to give yourself a headache trying to listen to simulated brain noise.
Definitely not.
Okay, so wrapping this up, we've taken this deep dive into an interactive EEG simulation, seen how it tries to demystify these complex brain signals using tools like PCA and ICA.
Yeah, showing those elegant mathematical solutions in action.
We've looked at its clever visual tricks, had a bit of a chuckle at its ironic limitations like signals outside the head.
And appreciated that constant push to make these tools better, more realistic, more useful for understanding the brain.
It really is fascinating because even as we build these incredibly sophisticated tools to map what's going on inside our heads,
We're constantly learning
That's
more,
right.
not just about the brain, but about the whole process of observing and interpreting complex data. How do we know what we know?
Exactly. Which kind of leaves us with a final thought, maybe. In a world that's just saturated with information, so much noise everywhere, how much better can we get at unmixing the signals? Not just from EEG data, but from, our own complex lives and the world around us. How do we get better at telling the real insight apart from just the noise?
That's the big question, isn't it? A really important one to keep asking.
Yeah, there is a human in the loop if you were wondering, if you have any questions, especially if you checked the website. Do let me know if you have any requests, complaints, likes, unlikes, dislikes.
I see a web page titled Multi-Pendulum Drawing Game. It shows a complex drawing created by multiple pendulums with different colors and settings, and there are controls for adjusting the pendulums. Based on the image, this doesn't appear to be directly related to biomedical data. It looks like a game or simulation demonstrating the movement of pendulums and the patterns they create. Well, if you consider the patterns generated by the pendulums as complex systems, it could be conceptually related to the analysis of biological signals or systems in biomedical research. For example, the motion could be analogous to the variability in physiological data or the dynamics of certain biological processes. The complex patterns generated by the pendulums could be analyzed using AI techniques. AI algorithms could be used to model the nonlinear dynamics of the pendulums, predict their behavior, or identify patterns in the drawings that might be difficult to discern manually. This involves principles related to machine learning and complex system analysis, which are key parts of AI. To improve the simulation, several enhancements could be made. Adding more pendulums with customizable properties, such as length, angle, and damping, could create even more complex patterns. Implementing more advanced physics models for realistic motion and allowing for interaction between the pendulums could further enrich the simulation. Additionally, adding features for data export and analysis would make it more useful for scientific research or exploring complex systems. All right, to summarize, the screen shows a multi-pendulum drawing game that creates complex patterns using multiple pendulums. While not directly biomedical, the simulation of complex systems can be related to analyzing biological data and AI-driven analysis. Improvements could include more complex physics, increased interactivity, and enhanced data analysis features.
Welcome to the deep dive. So, for those of us keeping an eye on generative AI, especially in creative spaces, today's topic is really interesting. It's called the Generative Doodle Game V4 with Creativity Slider. Now, we've seen AI image generators, sure, and style mimics, but this specific combo, generative plus a literal creativity slider, well, makes you think, right? About control, about what the AI is actually doing.
Exactly.
So our mission for this deep dive is basically to unpack what this thing means for creativity, for how we interact with these tools.
And it really touches on, fascinating intersections. Tech, art, human-machine collaboration.
Yep.
It's all in there.
Yeah, it feels like it forces us to look at creativity itself a bit differently. Is it the person doodling, the AI interpreting, or like the whole process?
That's the core question, isn't it? It hints at something beyond just software.
Okay, let's get into it then. A generative doodle game. How is that fundamentally different from, say, just a normal drawing app on your tablet? What's the generative part really do?
Right. So generative here means the system isn't just a passive canvas. It's actively creating or modifying based on what you put in.
Oh.
It uses, algorithms, often complex ones, that have learned patterns from tons of data. It's not just applying a simple filter. It's predicting, creating new stuff based on your doodle.
So it's less like a brush and more like a collaborator, an assistant.
An artistic co-pilot is a good way to think about it. You give it a seed, your doodle, and it grows something from it. It can infer, extend, sometimes even totally reinvent your idea.
A co-pilot. I like that.
Yeah.
Which brings us to the really intriguing part, the creativity slider. And it's specifically noted as being set at 50%.
Yeah.
A creativity percentage. That sounds, well, how do you even quantify creativity like that? What does 50% mean in practice?
Yeah, that's the million-dollar question, isn't it? It immediately brings up these deep issues about, agency. Who's in charge here?
Right.
So that slider, think of it as a dial for how much the AI gets to interpret or even deviate from what you drew. At 0%, it might stick really close to your lines. Maybe just cleans them up, adds a subtle texture, something like that. But if you crank it up towards 100%, it could take your simple circle and, who knows, see a face, or build a whole landscape from just a squiggle.
Wow.
You're essentially controlling the level of, let's say, algorithmic unpredictability, how much freedom you're giving the AI to think outside the box based on your prompt.
So you're dialing in the AI's temperament, its willingness to go wild.
Sort of, yeah, it's interpretive freedom.
That's kind of mind-bending. And speaking of interpretation, the game also lists specific artist-style options. Van Gogh, Picasso, Kandinsky, pointillism. I mean, that's amazing. You doodle something basic, and it can render it like Van Gogh.
Exactly, and that highlights the sheer complexity and power we're talking about.
Yeah.
The system doesn't just see lines. It has to understand the essence of Van Gogh's swirling strokes or Picasso's fractured perspectives or Kandinsky's abstraction.
How does it even learn that?
Through massive amounts of training data, essentially learning the grammar of each style. So it lets you, the user, take your own simple sketch and instantly see it reimagined through these totally different iconic lenses.
Them artistic playground. See your house sketches of Kandinsky.
Or your dog done by Picasso, yeah. It offers this immediate stylistic translation, which is, well, it was impossible on this scale before.
It's fascinating. But then, even with all this AI power generating, interpreting, stylizing, they still include basic buttons like undo, clear, save. That seems important.
It's absolutely critical.
Does that mean, even if we want the AI's help, we still need that final say?
Where's it?
Exactly. It shows a design philosophy where the human is still firmly in the loop. The AI is a powerful co-creator, yes, but these tools acknowledge your intent, your desire for control. It means you're not just passively watching the AI, you're actively curating, collaborating. You can nudge it, undo its suggestions, save what you like. It ensures the final thing still feels like yours, even with the AI's heavy involvement. Right, so pulling back a bit, this whole generative doodle game thing seems to be this really unique mix. It's your input, but then there's this sophisticated AI generation layered on top.
Yeah.
And crucially, you have these explicit controls over how it interprets the style and even this abstract creativity level.
And that's where it gets really interesting, looking bigger picture. This kind of tool, it really starts to challenge our old ideas about authorship, right?
How so?
Well, if the AI turns your simple doodle into something amazing in Van Gogh's style, who's the artist?
Yeah.
You, the AI, the original artist whose style was learned. It blurs those lines.
Yeah, I see that.
It makes us ask, is creativity just a human thing, or can it be something that emerges from these complex algorithms interacting with us?
Yeah.
It definitely pushes the boundaries between the artist and the tool.
That is a deep thought, not just for art, but really any creative work. So, okay, maybe a final thought for you listening. Next time you're sketching, brainstorming, whatever, Think about this. What if you had a tool where you could literally dial creativity up or down, or instantly see your idea through the eyes of a master? How might that change how you approach creating things, or even just solving problems?
Yeah.
Well, it's a pretty exciting frontier to think about. Welcome, curious minds. Today, we're embarking on a deep dive into a really remarkable platform called BioniChaos. You should think of it like a digital sandbox, really, where biomedical data, cutting-edge technology, and education all sort of playfully collide.
Yeah, it's fascinating. And what's truly compelling about BioniChaos, I think, is its core mission, which is basically to make the incredibly complex world of biomedical data processing accessible to everyone.
Exactly.
They're effectively, democratizing insights that were maybe once locked away in very specialized labs.
And when we say everyone, we really mean it. I mean, sure, it's a gold mine for researchers, educators, students, biomedical engineering, neuroscience folks. But honestly, even if you're just deeply curious, like us, you're going to uncover some pretty profound aha moments here.
Definitely.
Our goal today is basically to give you a shortcut, a way to get well-informed on what's possible in this space.
Right.
Navigating through this fascinating world of biomedical tech without feeling, completely overwhelmed.
Which is easy to do in this field.
Oh, absolutely. So let's start right at the foundation, the biomedical signals themselves. BioniChaos introduces this with a really fantastic modality comparison bubble chart. It visually explains things like temporal and spatial resolution.
Yeah, and just pausing on that for a second, understanding those distinctions, like how quickly and how precisely different signals capture information, that's absolutely crucial.
Crucial how?
Well, it dictates which tools and techniques are the right ones for any given research or application. It's not just what data you collect, but how it's kept as the nuances of where it comes from. That really matters.
Okay, right. And this is where BioniChaos, I think, genuinely transforms these abstract ideas into something tangible. They're interactive simulators.
Yes, the simulators.
Those aren't just static diagrams. You're actively, engaging with the data.
You're playing with it.
Exactly. Take the advanced EEG signal simulator. So EEG, that's electroencephalography. Basically measuring the brain's electrical whispers from the scalp.
Tiny little signals.
Tiny signals. And this simulator lets you customize different brainwave frequencies, delta, theta, alpha, beta.
Classic bands.
Right. And then you see them in real time across time and frequency domains. You can even simulate common artifacts like eye blinks, muscle movement.
Which are the bane of EEG researchers everywhere.
Totally. And you see how they mess up the data. It's not just theory. It gives you this profound insight into how things like brain-computer interfaces, BCIs, actually work by targeting specific frequencies.
That level of direct manipulation is incredibly powerful for learning, isn't it?
It really is.
It makes me think about those core concepts that are often just, static images in a textbook. Here, you're not just reading about brainwaves.
No.
You're actively experimenting with them, generating those aha moments you mentioned.
Exactly. And BioniChaos doesn't shy away from those foundational concepts either. They really nail things like the nuances of impedance in EEG.
Which is super important.
Yeah. And impedance here isn't just simple resistance. It's about how well those electrodes on your scalp actually pick up the brain signals through your skin. Yeah. It's crucial for getting clear data.
Absolutely. Garbage in, garbage out, right?
Pretty much.
Yeah.
And they also emphasize the critical role of understanding sampling rates. That's how many times per second a signal is recorded. Like for EDA skin conductance, or PPG, the pulse signal. Capturing enough data points is just vital for seeing those subtle physiological changes.
Yeah.
You miss things if you don't sample fast enough.
Yeah, you lose the detail.
Okay, so it's one thing to understand the signals, but how do we translate that knowledge into, real-world impact?
Right, the application.
The journey from, wiggly line on a screen to a life-changing diagnosis. That's where BioniChaos really connects the dots. Let's explore how these tools help with actual health challenges, maybe starting with epilepsy management.
Yeah, that's a great example. It's an area with just profound implications for millions of people, and the ability to move beyond basic signal stuff to real clinical scenarios is where platforms like this become, indispensable.
So for epilepsy, what have they got? Well, there's a fantastic interactive evidence review on epilepsy and cardiac health. It compares how different anti-epileptic meds affect the heart.
Which is a really important side effect to monitor.
Definitely. Then for seizure detection, tools like Rhythm Scan let you explore actual EEG data and see how machine learning can identify seizure activity.
So you're not just told ML finds seizures, you can sort of see how.
Exactly. And Seizures Zone, this is cool, it's a 3D brain mapping visualizer.
Yeah.
You can explore specific brain regions, see their functions in relation to where seizures might originate or spread. It helps visualize it.
That kind of visualization is key. This whole comprehensive approach really highlights not just the potential of EEG in epilepsy, but also its limitations, when used alone. And why combining it with other data, other modalities, is often crucial for getting the full picture.
Right. Makes sense.
And it's also neat that they highlight milestones like the 100 years of EEG celebration. It underscores its, enduring impact on neuroscience.
Yeah, a century of brainwave studies. And speaking of cutting-edge stuff, there's a fascinating deep dive into brain-computer interfaces, or BCIs.
BCIs, always exciting.
BioniChaos features the Stentrode. That's the minimally invasive BCI from Syncret Inc.
Right, the one that goes in through blood vessels.
Yeah, and its potential for decoding motor intent, basically. Thoughts about movement in patients with ALS.
That innovation is truly groundbreaking. I mean, allowing individuals with severe paralysis to communicate or control devices just using thought.
It's incredible.
But it also immediately brings us to the ethical landscape, doesn't it? Which emerges alongside such powerful neural implants.
Absolutely. There are big questions.
And BioniChaos thoughtfully explores this. They have a piece, Advancing Neurotechnology, the Impact and Ethics of AI-Enhanced Brain-Computer Interfaces. It gets into critical issues, data privacy, informed consent, equity, who gets access, and even questions of personal identity.
Right. As human and machine interfaces get more seamless, what does that mean?
Exactly. Big, important questions.
Okay, so beyond brain activity, they also cover hearing and vision with some brilliant interactive tools.
Oh, interesting.
There's a cochlear simulator and an interactive cochlear implant insertion simulator visualizing how those devices work. You even use their hearing aid simulator.
So you can experience different levels of amplification.
Yeah, or take an interactive hearing test right there, measure your own hearing threshold, download an audiogram.
Wow, okay.
And for vision, their vision impairment simulator. This lets you experience conditions like myopia, nearsightedness, and glaucoma in real time.
That sounds like a powerful tool for building empathy.
It really is. An eye-opening way, literally, to build understanding. And then, shifting gears a bit, in the world of medical devices, BioniChaos provides an insightful summary of recalls from 2017 to 2024.
Oh, that's important context to the reality of medtech.
It is, and there's a particularly compelling case study, Seer Medical. They were a startup, revolutionized epilepsy diagnostics,
I remember them.
faced a catastrophic recall, but are now apparently on a path to recovery. It's just a powerful story that really brings home the real-world stakes. Yeah.
Absolutely. The triumphs, the setbacks, the pressure. It's all part of innovation in healthcare.
Exactly. The relentless pursuit of innovation for patient care with all its challenges.
Yeah.
Now, as we move from understanding signals and applications, I found myself particularly fascinated by how BioniChaos integrates, well, AI and machine learning.
The buzzwords, but important ones here.
Right. They show how these technologies are genuinely revolutionizing biotech, specifically looking at how AI and machine learning are transforming EEG and ECG analysis.
And what this means for the bigger picture is that AI, machine learning, advanced computing, they aren't just abstract ideas anymore.
No.
Their interactive Venn diagram of AI types is great for this. It
Right.
clearly shows how these fields overlap and how they specifically apply in healthcare, moving from theory to, actual practical use.
They even look at AI's role in scientific communication with something called ChatGPT Author.
Oh, interesting. How so?
Well, it highlights both the incredible potential for speeding up research dissemination, but also the crucial challenges of maintaining academic rigor when you're using AI tools for writing or analysis.
That's a very current debate.
Very. And there's another piece on bridging engineering and clinical language with AI.
Yeah.
It shows how AI, especially large language models, can actually help engineers and clinicians talk to each other more effectively.
Which is a huge barrier sometimes. Different languages almost.
Totally. So AI as a translator, that could be a huge leap for interdisciplinary work.
Definitely need it.
Now, a crucial part of all this data, AI or not, is how we look at it, right?
Mhm.
Visualization.
Can't emphasize that enough.
The data source does in visualization on their site is just a fantastic example.
Okay.
It shows something deceptively simple, but so powerful.
What's the concept?
You could have a dozen different data sets. They all have the exact same averages, standard deviations, correlations. Basic summary stats are identical.
Okay.
But when you visualize them, they look completely different. One looks like a dinosaur, others are circles, lines, totally different distributions hidden behind the same numbers.
Wow. Okay. Yeah, that powerfully makes the point. Summary stats alone can be really misleading.
Absolutely. It hammers home why seeing your data is essential for finding those hidden patterns and, frankly, avoiding big mistakes.
It really begs the question, are we truly understanding the data if we're not visualizing it properly?
Right.
It underscores that whole idea that knowledge is most valuable when it's not just understood theoretically, but when you can effectively apply it, analyze it critically, see the hidden truths.
Couldn't agree more. And, it's not just about complex biomedical signals and high-level AI on BioniChaos.
Oh, what else?
They also work to democratize just general learning and scientific exploration in ways you might not expect.
Like how?
Well, for instance, practical tools like PaperViz. You can upload a research paper PDF, and it helps you visualize and explore the extracted content.
Handy for tackling dense papers.
Yeah, and the PDF extractor just does what it sounds like, pulls out text quickly. These are just useful tools for any learner, really.
Practical utilities, yeah.
They even get into something called mental health engineering.
Mental health engineering.
Yeah, showing how engineering concepts, signal processing, simulations can actually be applied to model the complexities of mental well-being.
That's a fascinating angle, applying engineering frameworks to mental health.
Offers new perspectives on a really crucial area. But here's where BioniChaos, I think, truly breaks the mold. They make learning genuinely fun.
Fun. How so?
Forget dry textbooks for a minute. Imagine playing a game called Dopamine, where, every click gives you a little reward. And through that, you explore reaction time and memory.
Ah, gamification.
Totally. Or seeing how easily your brain can be tricked by optical illusions like the Ponzo illusion or something called Bounce Viz.
Okay, like science museum exhibits almost.
Exactly. They might seem like simple games, but they're really cleverly designed. They demonstrate fundamental principles, perception, physics, even reinforcing ideas about human-computer interaction.
So they make complex ideas engaging and memorable through play.
Precisely. It's like a high-tech arcade for your brain that's subtly teaching you science along the way.
That really showcases their commitment, doesn't it? Making learning accessible, showing complex ideas through these playful, interactive experiences.
Yeah.
It reinforces that idea that there's always more to learn and that multiple perspectives, even from, seemingly simple games, can really enrich our understanding.
Okay, so let's try and unpack this a bit. BioniChaos offers this incredible array of interactive tools, resources, all designed to make biomedical data accessible, engaging, and deeply understandable.
Yeah, it really exemplifies how knowledge becomes most valuable when you can actively explore it, apply it, examine it critically. It encourages that deep critical thinking across really diverse and complex fields.
It does.
I mean, it's an incredible start, this democratization of access. But of course, mastering these fields still requires, dedicated practice and critical thinking beyond the platform's initial guidance. It's a launch pad.
A fantastic launch pad, though. Whether you're a student maybe prepping for a meeting or someone just trying to catch up on a new field or, just insanely curious, these tools offer a unique path to understanding really complex biomedical concepts without feeling completely lost or overwhelmed. It truly is a kind of shortcut to being well-informed.
I agree.
So the final thought, then. What does this all mean for the future of learning itself? How might interactive, simulation-based platforms like BioniChaos redefine the future of scientific education, not just in biomedicine, but maybe across all STEM fields? What stands out to you as you think about that?